There is no such thing as a natural desert in Australia, not in the way we have been taught to think about it, not as an original condition of the land, not as the inevitable product of climate alone, not as proof that this continent was always too harsh, too dry, too unforgiving for anything but the most minimal forms of life. What we call the Australian desert today is not a beginning, it is an ending. It is what remains after something extraordinary was cut down, burned out, grazed to the bone, and replaced with dust and silence. It is the scar tissue of a continent that was, within living geological memory, a different world entirely. A world of forests so dense they would be unrecognizable to anyone who has only ever seen the Australia of the last 200 years. A world of rivers that ran clear and permanent. A world of grasslands so thick with life that the animals living in them have no modern equivalents anywhere on the planet. A world that a civilization of extraordinary intelligence and patience maintained for 60,000 years, and that a different civilization destroyed in roughly 150. The story of the Australian desert is not a story about geology. It is not a story about rainfall patterns or solar radiation or the cruel indifference of a continent positioned in the wrong latitude. It is a story about what happens when you remove the living systems that held a landscape together. It is a story about the relationship between vegetation and rainfall. It is a story about soil and what lives in it. It is a story about fire and what happens when you stop using it the way it was meant to be used. It is, when you follow it all the way down, a story about what civilization actually means. And it raises the most uncomfortable possible question about which peoples, in the long record of human habitation on this continent, actually understood the word. Subscribe now. Turn on notifications, because what you are about to hear is going to change the way you look at every landscape you have ever called natural. Number one, the living continent that we buried. 40,000 years ago, Australia was not a desert continent. It was a green one, not uniformly green. The interior had always been drier than the coasts. The Pleistocene climate was variable, and the continent's position meant it received less consistent rainfall than tropical land masses at different latitudes. But the interior of Australia before European contact, and for tens of thousands of years before that, was not the relentless red wasteland that tourists photograph from aircraft windows, and that the rest of the world has come to accept as the natural Australian condition. The interior carried vast grasslands thick enough to support megafauna, giant animals that existed nowhere else on Earth. The grasslands were maintained by a complex of rainfall patterns, soil biology, and most critically, a fire management regime practiced by the continent's human inhabitants with a sophistication that took thousands of years to develop, and whose disruption would, within a few generations of being abandoned, transform the landscape permanently. The archaeological and paleobotanical record of the last few decades has overturned much of what was believed about pre-European Australian vegetation. Pollen cores taken from lake sediments across the continent reveal that areas now occupied by desert scrub and bare stone were, within the last 10 to 15,000 years, carrying significantly denser vegetation. The Flinders Ranges, now an iconic landscape of red rock and sparse saltbush, were forested to an extent that modern Australians would find difficult to recognise. The Nullarbor, now so bare that its Latin name, no tree, is taken as self-evident description, showed evidence of significantly more complex vegetation within time frames that are not geological abstractions but human history. The continent was not unchanging before Europeans arrived. Climate did shift, rainfall patterns did vary. The megafauna extinction that occurred around 45,000 years ago, a complex event whose exact causes are still debated, changed the grazing pressures on grassland ecosystems in ways that had lasting effects. But the baseline condition of the Australian interior at the time of European contact was not the degraded, unstable landscape we see today. It was a landscape that had been managed by human intelligence for thousands of years, and that bore the marks of that management in ways European observers were systematically unable to recognize. What happened after European settlement was not the simple revelation of Australia's true harsh nature. It was the destruction of the management systems that had maintained the landscape in a livable state, followed by the introduction of grazing regimes and land clearing practices that accelerated and amplified the degradation to a point where natural recovery became impossible without active intervention. The desert that tourists photograph today is not ancient. It is recent. It is the wound, still open, of a civilization destroyed. Number 2, the megafauna and what their disappearance should have told us. Before we can understand what Australian landscapes were like under proper management, we need to understand what lived in them and what the loss of that life meant for the systems that supported it. The Australian megafauna, the collection of giant animals that went extinct roughly 46,000 years ago, were not just impressive curiosities of the fossil record. They were ecological engineers. Their feeding habits, their movement patterns, their dung, their grazing pressure, and their physical interaction with the landscape shaped the vegetation communities that existed around them in ways we are only beginning to fully understand. Diprotodon optatum, the giant wombat, was the largest marsupial ever to live. It stood roughly 2 meters at the shoulder and weighed as much as 2.5 tons. As a large herbivore with enormous digestive capacity, it would have consumed and processed vegetation at a scale comparable to modern rhinoceros or hippopotamus populations. Its dung alone would have been a significant nutrient cycle driver, moving nutrients from consumed plants back into the soil across the ranges it traveled. Procoptodon goliath, the giant short-faced kangaroo, stood 3 meters tall and weighed around 200 kilograms. Unlike modern kangaroos, its teeth were adapted for browsing on tough shrubs and low trees rather than grazing on grass. It was a tree pruner at a scale that no living Australian animal approaches. Its browsing would have maintained the open woodland and grassland edges that many other species depended on. Thylacoleo carnifex, the marsupial lion, was the largest carnivorous mammal Australia ever produced. Its role as an apex predator shaped the behavior and distribution of the grazing and browsing animals it hunted, which in turn shaped the way those animals interacted with the vegetation. Remove the apex predator, and the herbivores change their behavior. They graze differently, they move differently. The vegetation responds to those different grazing patterns. The cascading effects of the megafauna extinction on Australian vegetation were profound and have been underappreciated in conventional discussions of Australian landscape history. When the large herbivores disappeared, the vegetation communities that had coexisted with them for millions of years lost the management pressures that had shaped them. Fuel loads in fire-prone landscapes built up without the consumption that large herbivores provided. Vegetation composition shifted as the browsing and grazing pressures that had maintained certain plant communities were removed. The landscape began a slow reorganization that the arrival of human fire management would partially compensate for, but never fully replace. What this means for understanding the Australian desert is this. The landscapes that European settlers encountered were already changed from their pre-megafauna state. They were already managed, but managed by human fire rather than by the combination of large herbivore grazing and human fire that had characterized earlier periods. They were productive and relatively stable, but that productivity and stability were maintained by practices that required constant attention. Remove the attention, and the landscape would degrade. And that is exactly what happened. The megafauna extinction was not a disaster from which Australia never recovered. Indigenous Australians adapted to a world without giant marsupials and developed fire management practices sophisticated enough to maintain productive landscapes for tens of thousands of years. But it left the continent more dependent on human management than it might otherwise have been. And when that human management was disrupted by colonization, the consequences were faster and more severe than they might have been if the megafauna had still been alive to help hold the landscape together. Number 3, fire as a technology of civilization. To understand why Australia's landscape degraded so rapidly after European settlement, you need to understand fire. Specifically, you need to understand what fire is when it is used correctly, and what it becomes when it is abandoned or misused. In the standard Western conception, fire is a destructive force. It is something that happens to landscapes. It is a threat to be suppressed, a disaster to be prevented, an emergency to be fought. The entire apparatus of modern fire management in Australia, with its emphasis on hazard reduction burns conducted at specific times under specific conditions, is a legacy of this conception. Fire is the enemy. You manage it to minimize it. The Aboriginal conception of fire is almost the opposite. Fire is a tool. It is the most powerful land management tool available, the one that can reshape vegetation communities at landscape scale, create habitat for specific animal species, clear old growth and promote new growth, drive game toward hunters, maintain travel corridors, signal between groups, and in skilled hands, do all of these things simultaneously with effects that persist and compound over years and decades. Cultural burning, the practice of deliberate controlled fire use as systematic land management, was not invented by Aboriginal Australians. Fire has been used as a land management tool by Indigenous peoples on every inhabited continent for tens of thousands of years. But in Australia, for reasons connected to the continent's specific ecology, the practice reached a level of sophistication, integration, and systematic application that is arguably unmatched anywhere else on Earth. The evidence for this is not primarily oral tradition, although oral tradition is consistent and detailed on the subject. The evidence is in the landscape itself, in the pollen record, in the soil record, in the tree ring record, in the charcoal deposits found in lake sediments across the continent, for tens of thousands of years before European contact. The charcoal record in Australian lake sediments shows a pattern of frequent, low-intensity fires that were clearly not the product of lightning strikes or natural ignition patterns. The fires were too frequent, too widespread, and too consistent in their timing to be natural. They were human. They were deliberate. They were managed. The plants of the Australian interior adapted to this fire regime over thousands of years. Many of them became dependent on it. The spinifex grass of the desert regions, for example, grows in clumps that become progressively less productive as they age, accumulating dead material in their centers while maintaining green growth only at the outer edges. Burning rejuvenates spinifex. It clears the dead material, stimulates new growth, and makes the grass productive again in a way that benefits both the plant and the animals that depend on it. Without periodic burning, spinifex clumps grow old and unproductive, and the animals that lived among them have nothing to eat. The same logic applies across the Australian flora with remarkable consistency. The continent's fire-adapted plants, the eucalypts, the acacias, the banksias, the grass trees, evolved in a world where fire was frequent and often deliberate, and many of them have reproductive strategies that require fire to be effective. Seeds that germinate only after being exposed to smoke or heat. Lignotubers that allow recovery from burning but not from prolonged grazing pressure. Bark adaptations that allow trees to survive repeated low-intensity burns that would kill plants from fire-naive environments. When Europeans arrived and began suppressing fire, they were not protecting a natural system from an unnatural disturbance. They were removing the management regime that had maintained the system for tens of thousands of years. They were, in the precise agricultural sense, letting the field go fallow without any plan for its recovery, and the field, in the specific ecological context of the Australian interior, did not recover on its own. It degraded. The fire-adapted plants whose productivity depended on regular burning became progressively less productive. The animals that depended on those plants declined. The fuel loads that regular low-intensity burning had kept manageable built up to levels that when they eventually did burn, produced catastrophic high-intensity fires that killed the mature trees rather than passing harmlessly beneath them. The European replacement of cultural burning with fire suppression was not a neutral substitution. It was the removal of the operating system that the Australian landscape had been running on for 60,000 years. Number 4, the sheep and what they did to the soil. If the suppression of cultural burning was the first blow to the Australian interior, the introduction of sheep was the second. And in terms of its direct physical effect on the landscape, it may have been the more devastating of the two. Australia has no native ungulates. No hoofed animals of any kind evolved on the continent during the millions of years of its isolated development as a separate landmass. The animals that did evolve there, the kangaroos and wallabies, the wombats, the bilbies, the native rodents, were designed by evolution to move across Australian soils in ways that do not compact and destroy them. Kangaroos have soft feet and a bounding gait that distributes their weight across a large area with each stride. They do not punch holes in the ground. They do not grind the soil surface to powder. They do not strip vegetation down to bare earth and then trample the exposed soil until it forms an impermeable crust. Sheep do all of these things. Hard hooves on soft soils create a compaction effect that reduces the soil's ability to absorb water. Rain that would have percolated into the soil under native animal management instead runs off the surface, taking topsoil with it. The vegetation that sheep graze is stripped far more thoroughly than native animal grazing strips it, because sheep can eat plants down to the root crown in a way that prevents recovery. The hooves that follow the grazing then trample the exposed soil, breaking up the biological crusts, the communities of cyanobacteria, lichens and mosses that form on the surface of desert soils, and that are among the most important water retention and soil stability mechanisms the desert ecosystem has. The biological soil crust of the Australian interior deserves more attention than it typically receives, because its destruction was arguably one of the most significant and least reversible consequences of sheep grazing on Australian desert landscapes. This crust forms on the surface of stable desert soils where it has not been disturbed. Under a microscope, it is a living community of extraordinary complexity. Cyanobacteria bind soil particles together with their filaments, creating a surface that is physically resistant to wind and water erosion. Mosses and lichens add further stability and contribute to the nutrient cycling that keeps desert soils functional. The crust is fragile in the sense that it can be destroyed by a single passage of a hard hoof, but it is also the product of decades of undisturbed growth, and once destroyed, it takes decades to recover under favorable conditions. In the first decades of European pastoral expansion across the Australian interior, sheep moved across landscapes carrying intact biological soil crusts that had been stable for thousands of years. As they moved, they destroyed those crusts. And as the crusts were destroyed, the soil beneath them became vulnerable to wind erosion in a way it had not been before. The dust storms that began to characterize the Australian interior from the mid-19th century onward were not a natural phenomenon. They were the pulverized remnants of the topsoil that had taken thousands of years to accumulate, being lifted by the wind and blown into the ocean. The topsoil loss of the Australian interior in the century and a half following European settlement was not measured carefully enough at the time for us to have precise figures, but estimates based on current soil depth comparisons with areas that have been less heavily grazed suggest that significant portions of the pastoral zone lost tens of centimeters of topsoil in a period of 1 to 2 generations. That topsoil will not recover in any time frame relevant to human planning horizons. Soil formation rates in arid environments are measured in centuries per centimeter. The biological capital that sheep grazing destroyed in decades will require centuries to restore under ideal conditions and longer in the degraded conditions that persist after the grazing pressure is removed. The relationship between sheep numbers and landscape capacity was understood by some observers relatively early. By the 1880s, there were pastoralists writing about overgrazing and its consequences with a clarity that suggests the destruction was already visible to anyone paying attention. The problem was that the economic system within which Australian pastoralism operated rewarded maximum stocking rates in the short term and externalized the long-term costs of degradation onto the landscape itself. The land could not lobby Parliament. The sheep could not vote. The people who had lived on and managed the land for 60,000 years had been dispossessed of both their land and their political voice. And so the stocking rates remained too high, and the degradation continued, and the desert expanded. Number 5, what water does when you remove the trees. There is a relationship between trees and rainfall that is still not fully understood by science, but whose importance is becoming clearer with each decade of research. Trees do not merely respond to rainfall, they participate in creating it. The process by which forests generate and recycle their own rainfall is called the biotic pump. It is a hypothesis developed by Russian physicists Anastasia Makarieva and Viktor Gorshkov in the early 21st century. And while it remains somewhat controversial in the details, its general outlines are supported by a growing body of observational evidence from deforested regions around the world. The basic mechanism is this. Forests transpire enormous quantities of water into the atmosphere. A single large eucalyptus tree in a productive environment can transpire hundreds of liters of water per day. That water enters the atmosphere as water vapor, which eventually condenses and falls as rain, often over the same forested area or in the region downwind from it. Forests, in this model, are not passive recipients of rainfall delivered by distant atmospheric systems. They are active participants in the water cycle, pumping water from the ground into the atmosphere through their roots and leaves, contributing to the formation of clouds and the generation of precipitation, and creating microclimates around themselves that make rainfall more likely and more frequent than it would be in the absence of vegetation. Remove the trees and you remove the pump. The water that the trees were transpiring into the atmosphere is no longer there. The rainfall patterns that depended on that transpiration change. Less water enters the atmosphere from the land surface, so less water precipitates back onto it. The landscape dries, and as it dries, the remaining vegetation comes under moisture stress, which reduces its own transpiration, which further reduces the moisture available for rainfall, which further stresses the vegetation in a feedback loop that can be very difficult to reverse once it gains momentum. The clearing of Australian woodland and forest for agriculture and grazing represents one of the largest and most rapid vegetation clearance events in the history of human land use. Australia has one of the highest land clearing rates in the world even today. In the century following European settlement, vast areas of woodland that had been stable for thousands of years under indigenous management were cleared for agriculture in the southeastern wheat belt, for grazing in the semi-arid pastoral zone, and for timber in the coastal ranges. The consequences for regional rainfall patterns were not immediately obvious, because the relationship between vegetation and rainfall operates over spatial and temporal scales that make simple cause and effect difficult to observe directly. But the long-term rainfall records now available for much of Australia tell a story. Many inland regions of Australia have recorded declining rainfall trends over the period since European settlement and land clearing. The decline is not uniform and cannot be attributed solely to vegetation change, as climate variability operates on its own schedules independent of human activity. But the correlation between land clearing and declining rainfall is strong enough in some regions to be difficult to dismiss as coincidence. The wheat belt of Western Australia provides perhaps the most dramatic example. This region underwent massive clearing of native mallee woodland through the 20th century for dryland wheat production. The consequences were catastrophic in ways that had nothing to do with rainfall and everything to do with hydrology. Clearing the deep-rooted native vegetation lowered the rate at which water was being transpired from the soil, causing the water table to rise. As the water table rose, it brought ancient salt deposits close to the surface. The result was dryland salinity, the emergence of salt in the soil profile at concentrations toxic to most plants, rendering cleared agricultural land sterile. By the late 20th century, millions of hectares of Western Australian agricultural land were affected by dryland salinity, with the problem continuing to expand. The economic losses were enormous. The ecological losses were worse. The communities of native plants and animals that had lived in the cleared woodland were gone, replaced first by agriculture, then by salt-poisoned wasteland that supported almost nothing. The clearing had destroyed the very thing that made the land productive. It had removed the trees that were managing the hydrology, And without those trees, the water that rainfall delivered was no longer being used efficiently. It was accumulating underground, mobilizing salt, and destroying the soil's capacity to support any life at all. Number 6, the rivers that died. Before European settlement, the rivers of the Australian interior were different from what they are today. Not in every case and not uniformly, but the pattern is consistent enough across multiple river systems to constitute a story rather than a collection of isolated incidents. The Murray-Darling River System, the largest and most significant river system in Australia, draining roughly 1 million square kilometers of the continent's interior, was a different system in the 18th century from what it is today. The riverbanks were held in place by the roots of dense riparian vegetation, ancient river red gums, and black box communities that had established themselves over centuries and that bound the bank soil together against erosion. The floodplains were covered with native pasture grasses and forbs that intercepted rainfall and regulated runoff in a way that kept the rivers running more consistently through the seasons. The wetlands connected to the river system provided nursery habitats for native fish and filtering functions that kept the water clear. The riparian vegetation was part of a larger system. The reed beds and swamp plants that colonized the shallow edges of the river and its connected wetlands were not just picturesque. They were water filters, trapping sediment and nutrients and keeping them from accumulating in the waterway. They were habitat for the fish and water birds that depended on the river system. They were the living edge of the water's relationship with the land. Sheep and cattle destroyed this edge. Heavy grazing along riverbanks stripped the riparian vegetation and left the bank soil exposed. Without plant roots holding it together, the banks began to collapse into the river. The eroded soil entered the waterway, increasing sediment loads and reducing water clarity. As water clarity declined, the aquatic plants that photosynthesized on the riverbed were shaded out. As those plants declined, the invertebrates that lived among them declined. As the invertebrates declined, the fish that ate them declined. The collapse of the riparian zone was a cascading ecological disaster that worked its way through the food web of the river system in ways that took decades to fully manifest. At the same time, land clearing upstream was changing the hydrology of the river system. Where native vegetation had previously intercepted rainfall and released it slowly through transpiration and infiltration, bare or sparsely vegetated cleared land allowed rainfall to run off rapidly into waterways. The rivers began to experience more extreme flood and drought cycles than they had under vegetated conditions. Floods were larger and faster because the cleared land upstream was delivering water to the river rapidly rather than releasing it slowly. Droughts were more severe because the slow water release from transpiring native vegetation was no longer buffering the dry periods. The extraction of irrigation water from the Murray-Darling system began in earnest in the late 19th century and has continued to expand throughout the 20th and 21st. By the early 21st century, the system was so heavily over-allocated that in dry years it did not consistently reach the sea. The mouth of the Murray was silting up. The lower lakes were becoming increasingly saline as reduced freshwater flows allowed salt water to intrude upstream. The wetlands of the lower river were dying. The blue-green algae blooms that became a recurring crisis in the Murray-Darling from the 1990s onward were the symptom of a system that had been fundamentally destabilized. Algae blooms thrive in slow-moving, warm, nutrient-rich water. European land use had delivered all three conditions simultaneously. The clearing and grazing of agricultural land had increased nutrient runoff into the river. The extraction of water had reduced flows and increased water temperatures. The destruction of riparian vegetation had removed the filtering systems that had previously kept nutrients out of the waterway. The result was a river that was chronically ill, episodically toxic, and fundamentally different from the system that had existed before European settlement. The rivers did not die suddenly or all at once. They died slowly, incrementally, over generations, in ways that made each individual step seem manageable and each loss seem like a natural adjustment rather than a symptom of systemic collapse. This is how ecological collapse usually works. It does not announce itself, it accumulates. Number 7, the grasslands that were a sea of gold. The early European explorers who penetrated the interior of Australia in the 19th century described something that later generations of Australians would have great difficulty imagining from looking at the same landscape. They describe grasslands, not the sparse degraded pasture that characterizes much of the current pastoral zone. Grasslands, dense, waist-high, continuous grasslands stretching to every horizon. Grasslands so thick with native species, Mitchell grass and wallaby grass and kangaroo grass and mulga grass and dozens of others, that the explorer Edward John Eyre described riding through grass that reached his horse's belly and stretched unbroken for hundreds of kilometers. Thomas Mitchell, exploring the Darling Downs and the open country to the south of it in the 1830s, wrote about pastures so rich and continuous that he called the country Australia Felix, Fortunate Australia, and predicted that it would become the garden of the continent. It became a desert instead. The transformation was not slow. In the pastoral zones that were settled with sheep and cattle in the second half of the 19th century, the change from perennial native grassland to degraded annual weed-dominated bare ground happened within decades. The first wave of settlers brought enormous numbers of animals to land, whose carrying capacity they had no way of accurately assessing. The native perennial grasses, which had evolved under the intermittent light grazing of native animals and the management of cultural burning, had no tolerance for the continuous, intense grazing pressure that sheep imposed. The perennial grasses of the Australian interior are the foundation of everything that lives above them. They are not replaceable by the annual grasses and introduced weeds that colonize the bare ground after they are destroyed. The perennial grasses have root systems that penetrate deeply into the soil, reaching moisture unavailable to shallow-rooted annuals. They grow year-round, providing continuous cover. They bind the soil against wind and water erosion. They cycle nutrients through their root systems in ways that maintain soil fertility over the long term. When the perennial grass cover is destroyed by overgrazing, the soil is exposed. Wind erosion begins. The light, fine-grained particles of topsoil, the most fertile layer, blow away first. What remains is coarser, less fertile material that annual weeds can colonize, but that the perennial native grasses cannot easily recolonize from seed. The land has crossed a threshold. It is not just degraded. It is on a different trajectory, one that leads toward less and less productive vegetation and more bare ground, not toward recovery. The speed of this transformation in the Australian interior during the pastoral era is one of the most dramatic vegetation changes documented in the human record. The grasslands that Edward Eyre rode through in the 1840s were stripped to bare ground in many areas within 20 years of intensive pastoral settlement. The plants that had maintained those grasslands for thousands of years, the perennial native grasses adapted to Australian soils and climate and fire regimes, were grazed to extinction across millions of hectares before most people in the settled South were aware that anything significant was happening. What replaced them was not a functional alternative ecosystem. What replaced them was degraded land in various stages of erosion, colonized by introduced weeds that provided minimal ecosystem function compared to the perennial native grasslands they had replaced, and that continued to destabilize as the soil erosion they could not prevent exposed more and more bare ground to the wind. The grassland destruction of the Australian pastoral era was not a development whose consequences were unforeseeable. The warnings came early. Pastoralists who had been on the land long enough to observe the before and the after wrote to newspapers and government committees in the 1870s and 1880s, describing the destruction they were witnessing and attributing it accurately to overstocking. The government committees they wrote to generally concluded that the solution was more scientific management of stocking rates, a response that acknowledged the problem while systematically underestimating its severity and the time it would take for the consequences to fully manifest. By the time the full consequences became visible, in the dust storms of the 1940s and 1950s, in the ration stations where dispossessed Aboriginal people survived on government handouts on what had been their own land, in the abandoned pastoral stations whose operators had finally given up on land that could no longer support enough stock to pay the bills, the grasslands that Mitchell had called Fortunate Australia were gone. They have not come back. Number 8, the soil biology that built the continent. Beneath the surface of any living soil, there is a world that makes the visible world above it possible. The soil biology of the Australian interior, the community of bacteria, fungi, nematodes, protozoa, earthworms, and other organisms that process organic matter into nutrients and nutrients into forms that plants can absorb, is one of the most important and least visible casualties of the processes that created the Australian desert. Soil is not a substrate, it is a community. A single teaspoon of healthy agricultural soil contains more individual organisms than there are people on Earth. A teaspoon of healthy native Australian grassland soil contains an even more elaborate community of specialists adapted to the specific organic matter and chemical environment of that particular ecosystem. These organisms are the engine of fertility. Without them, soil is merely mineral particles. With them, it is a living system capable of sustaining complex plant communities and the animal life that depends on those plants. The soil biology of the Australian interior evolved under specific conditions. It evolved under perennial native grass cover, which provided a continuous input of organic matter through root turnover and surface litter. It evolved under the fire regime maintained by indigenous land managers, which created pulses of nutrient availability that the soil organisms were adapted to respond to. It evolved under the light, intermittent grazing of native animals, which provided dung as nutrient input but did not compact the soil or strip the surface vegetation to a degree that disrupted the biological community below. European agricultural and pastoral practices disrupted this evolved system in multiple simultaneous ways. Cultivation mixed the soil layers, destroying the stratified communities that had established themselves in specific depth zones. Heavy grazing removed the organic matter input from surface litter and root turnover, starving the soil organisms that depended on it. Compaction by livestock hooves reduced the soil pore space that soil organisms and plant roots both require. The removal of native plant cover eliminated the mycorrhizal networks, the underground fungal connections between plants that are among the most important infrastructure of a functioning soil community. Mycorrhizal networks deserve special attention because they are among the most significant casualties of land clearing that is least understood by the public. These networks, which form between the roots of plants and the hyphae of specific fungal species, allow plants to share resources across distances far greater than any individual root system can reach. A tree connected to a mycorrhizal network can receive water and nutrients from plants hundreds of meters away. The mycorrhizal network is the nervous system of the plant community, and like a nervous system, its function depends on continuity. Clearing native vegetation destroys mycorrhizal networks. The fungi that form them require the specific plant partners they evolved with to survive. Introduce different plants or strip the vegetation entirely, and the fungal community changes. The mycorrhizal specialists that served the native plant community decline. The introduced agricultural plants, which either bring their own mycorrhizal associations or have been bred to function without them in artificially fertile agricultural soils, do not restore what was lost. The network does not recover when native vegetation is replanted because the fungal community that would form the network is no longer there to form it. The degradation of Australian desert soils through the destruction of their biological communities is an ongoing process that in many areas is still actively progressing. The restoration of degraded Australian rangelands is possible in principle, but requires both the removal of grazing pressure and the active restoration of soil biology in ways that current restoration practice is only beginning to understand. It is not a matter of stopping the degradation and waiting for natural recovery. It is a matter of actively rebuilding what was destroyed, using knowledge that we are still in the early stages of developing. Number 9, the water dreaming and what it knew. The indigenous peoples who managed the Australian interior for 60,000 years were not operating on instinct or habit. They were operating on the basis of an extraordinarily sophisticated knowledge system, developed through millennia of careful observation and refined through generations of transmission, that encoded detailed understanding of the relationships between vegetation, water, soil, and fire in a form that could be applied across the vast and variable landscape of the continent. The dreaming, the metaphysical and cosmological framework within which Aboriginal knowledge systems are organized is often misunderstood by people from outside the tradition as myth or religion in the Western sense, as stories about the supernatural that operate in a separate realm from practical knowledge about the material world. This misunderstanding has had consequences that extend far beyond the academic. The dreaming is not separate from the material world. It is a knowledge system encoded in narrative form that describes the material world with a precision that continues to astonish researchers who take the time to examine it carefully. Dreaming stories encode geological knowledge, biological knowledge, hydrological knowledge, and meteorological knowledge in forms that are simultaneously meaningful as spiritual narrative and accurate as practical information about specific landscapes. The water dreaming traditions of the arid interior are among the most practically significant of these encoded knowledge systems. In the Western Desert, dreaming tracks associated with water sources describe the locations, characteristics, and seasonal behavior of water in a landscape where knowledge of water is the difference between life and death. The tracks connect known water sources in sequences that reflect the actual hydrology of the landscape, the order in which rock holes fill and dry, the reliable versus seasonal sources, the underground sources that can be accessed by digging at specific locations. This was not mystical water finding. It was the accumulated practical knowledge of a people who had been navigating the same landscape for thousands of years, encoded in a form that could be transmitted to the next generation through ceremony and story rather than through written maps or manuals. The knowledge was as accurate and as practically useful as any map, and in some respects more so because it included information about seasonal variability and the relationships between water sources that no static map could capture. The knowledge systems that managed the Australian interior were not incidental to the productivity and stability of the landscape. They were essential to it. The cultural burning practices that maintained the grasslands were possible only because people knew precisely where and when to burn. Knowledge accumulated over generations and encoded in detailed lore about the specific fire behavior of specific country at specific times of year. The management of permanent water sources required knowledge of their catchment hydrology that allowed the people managing them to understand how they were being affected by conditions far away. The management of animal populations required knowledge of seasonal movement patterns, breeding cycles, and habitat requirements that no European naturalist had yet developed when settlement began. When colonization disrupted these knowledge systems by dispersing the populations that carried them, by killing knowledge holders, by disrupting the ceremonial contexts in which knowledge was transmitted, and by removing the people from the country whose management their knowledge had been developed to support. The consequences for the landscape were as real and as physical as the consequences of removing the vegetation or introducing livestock. The landscape lost its management system. It lost the intelligence that had kept it functional. And without that intelligence, it began to degrade. Number 10. The cattle and the north. If the story of the southeastern interior is primarily a story of sheep, the story of northern Australia is primarily a story of cattle. And the ecological consequences of cattle grazing in the tropical north are in some respects even more severe than those of sheep grazing in the temperate and semi-arid south, because the northern landscapes were, before European pastoral settlement, among the most biologically productive in Australia. The top end of the Northern Territory and the tropical savannas of Queensland, now characterized in many areas by degraded grasslands, introduced weed infestations, and cattle damage riparian zones, were, before the pastoral era, carrying an extraordinary diversity and density of wildlife. The floodplains of the rivers entering the Gulf of Carpentaria supported populations of water birds, reptiles, and mammals that early European observers consistently described with superlatives. The savanna supported marsupial populations whose diversity has not recovered from the hunting and habitat change that accompanied European settlement. The cattle entered northern Australia in a series of overlapping waves during the second half of the 19th century. The distances were enormous, the logistics were difficult, and the landscapes were unlike anything the drovers who moved the cattle had encountered before. The tropical wet-dry cycle of the north created conditions that were productive for much of the year. But that concentrated animals, both native and introduced, around shrinking water sources during the dry season in ways that produced intense localized grazing pressure precisely when the vegetation was most stressed. The riparian zones of the northern rivers, the thin strips of vegetation that grew along the banks of the rivers and billabongs, were particularly vulnerable. Cattle congregated around water in the dry season, and their concentration along river banks produced exactly the consequences that sheep had produced along the rivers of the south. Bank erosion, vegetation loss, sediment input to the waterway, decline of the aquatic ecosystem that depended on the riparian fringe for its integrity. The introduction of buffel grass, a tough African pasture grass introduced to improve cattle fodder in arid and semi-arid regions, created a separate disaster that is still unfolding across northern and central Australia. Buffel grass is extraordinarily effective at what it was introduced to do. It establishes quickly on bare ground, it grows rapidly and produces abundant biomass, and it is highly palatable to cattle. It is also extraordinarily effective at destroying the native ecosystems it colonizes. Buffel grass burns hotter than native grass. In a buffel-dominated landscape, a fire carries more energy and moves faster than in a native grassland. The fire regimes that native plant communities evolve to tolerate, and in many cases depend on, are replaced by a more intense fire regime that kills the native woody plants and animals that the native fire regime would have spared. The result is a landscape increasingly dominated by buffel grass itself, since buffel recovers rapidly after fire, while the native species that might compete with it do not. Buffel converts diverse native plant communities into monocultures of itself, and the animal communities that depended on the diversity do not survive the transition. The spread of buffel grass across northern and central Australia is one of the most significant ongoing ecological disasters in Australia today. It is largely invisible to urban Australians because it happens in remote country that most people never visit, but it is real and it is accelerating, and its long-term consequences for the Australian interior are severe enough that some ecologists describe it in terms of an extinction event in slow motion. Number 11. The disappeared animals and what they held together. When we talk about what the Australian desert has lost, we almost always focus on the plants and the soil and the water. The animals are less discussed, perhaps because the evidence of their former abundance is less physically visible on the landscape. But the animal communities that existed in the Australian interior before European settlement were integral to the functioning of the ecosystems that maintained the landscape. Their loss was not incidental to the landscape's degradation. In some significant ways, it was a driver of it. The small to medium-sized native mammals of the Australian interior are the species that have suffered the most catastrophic declines since European settlement. The bilby, the bettong, the quoll, the numbat, the native rodents, the bandicoots, these are species that were once common across vast areas of the Australian interior and that are now confined to small and often declining populations in isolated refugia. Many of them are extinct on the mainland and survive only on islands where foxes and cats have not penetrated. The ecological roles of these animals were not trivial. The bilby and other burrowing marsupials were soil engineers. They dug constantly, turning over soil in ways that aerated it, improved water infiltration, and buried seeds and fungal spores in ways that promoted plant regeneration. The volume of soil moved by a healthy population of bilbies across a large area is significant enough that their absence changes the physical properties of the soil in measurable ways. Areas that bilbies have been reintroduced to after long absences show measurable improvements in soil porosity and water retention within years of their return. The betongs and potaroos were fungal foragers, digging for underground fungi and in the process spreading the fungal spores that maintain mycorrhizal networks. The loss of these animals from the Australian interior removed one of the primary dispersal mechanisms for the fungal community that sustains plant root networks. The decline of the mycorrhizal network that followed contributed to the reduced capacity of native plants to recolonize degraded areas. The native rodents, often overlooked in discussions of ecological conservation because they are small and inconspicuous, were seed dispersers of enormous importance. Many Australian plant species have seeds too large or too heavy to be effectively dispersed by wind, and that evolved to be moved by small mammals. The loss of those mammals has left those plant species with reduced capacity to colonize new areas or to recolonize areas where they have been removed by fire, grazing, or clearing. The story of what removed these animals is well enough known. Foxes and cats introduced to Australia without any of the ecological context that constrained their population growth in their places of origin. The fox was deliberately introduced for hunting in the 19th century and spread across the continent with catastrophic speed. The cat arrived with the earliest European settlers and has been expanding and diversifying ever since. Both are extraordinarily effective predators of the small to medium-sized ground-dwelling mammals that constitute the middle layer of the Australian mammal fauna, and neither has any natural predator in Australia capable of controlling its population. But the story of the animals is also a story about the landscape that was lost and what the animals needed to survive in it. The native mammals of the interior evolved in landscapes with dense ground cover, with refugia and spinifex, and dense native grass from which they could not be easily run down by a predator. They evolved in landscapes where the cover provided by intact perennial grassland gave them enough shelter to detect and escape predators before the predators could close the distance. When overgrazing and the resultant vegetation loss stripped the ground cover from the landscape, the small mammals that had depended on that cover for their survival lost the refuge that evolution had told them was there. Foxes and cats, moving through a landscape with no hiding places, could hunt with a ruthless efficiency that was simply not possible in intact native grassland. The introduction of exotic predators and the destruction of native ground cover habitat are not separate stories. They are aspects of the same story. The predators could not have done what they did to the native mammal fauna if the habitat that protected that fauna had remained intact. The habitat destruction made the predators catastrophically more effective, and the predators made the habitat destruction catastrophically more consequential. Together, they reduced the animal communities of the Australian interior to a fraction of what they had been within a century of European settlement. Number 12. The knowledge that survived and what it is telling us. Despite everything that has been described in this script so far, the news is not entirely dark, and the reason it is not entirely dark is that the knowledge systems that managed the Australian landscape for 60,000 years were not entirely destroyed by colonization. They were diminished, disrupted, dispersed, and in many places severely damaged, but they were not erased. And what remains of them is increasingly being recognized as among the most valuable scientific resources available to anyone trying to understand how the Australian landscape worked before it was degraded and how it might be helped toward recovery. The revival of cultural burning is the most visible and perhaps the most immediately significant of these returns to Indigenous knowledge. Across northern Australia and increasingly in southern fire-prone regions, Aboriginal land managers and their scientific collaborators have been demonstrating for several decades now that cultural burning, conducted with traditional knowledge of the landscape, the season, the wind, and the desired outcome, produces ecological results that no other fire management technique can replicate. The work done by Aboriginal rangers in Arnhem Land through the West Arnhem Land Fire Abatement Project demonstrated not only that cultural burning maintained the diversity and productivity of the savanna landscape, but that it reduced the frequency and intensity of the late season high-intensity wildfires that characterize landscapes managed without traditional burning. The project generated carbon credits by demonstrating measurable reductions in greenhouse gas emissions from wildfire compared to business as usual fire management. It was the first program in the world to generate carbon credits from fire management on a national registry, and it proved that traditional knowledge translated into practical management action could deliver measurable environmental and economic outcomes in a framework legible to Western governance. The recognition of Aboriginal ecological knowledge in the management of Australia's landscapes is no longer fringe. It is increasingly mainstreamed into conservation policy, land management practice, and scientific research. The establishment of Indigenous protected areas, the growth of the Ranger program, the incorporation of traditional knowledge into national park management plans, the collaboration between Aboriginal knowledge holders and scientists in research into landscape history and ecology. These are signs that the relationship between Australian institutions and the knowledge systems that manage the continent for 60,000 years is changing. It is changing slowly. The changes are uneven. There is still resistance in some quarters to treating Indigenous knowledge as equivalent in validity and authority to Western scientific knowledge. A resistance that is becoming harder to maintain in the face of accumulating evidence that Indigenous knowledge is often more accurate, more detailed, and more practically useful for Australian conditions than anything Western science has so far produced as an alternative. But the direction of change is clear, and the pace of change is accelerating. The knowledge holders who remain, the elders who still carry detailed traditional knowledge of country and its management, are increasingly in demand as partners in environmental restoration projects across the country. They are being consulted, listened to, and in the best projects, genuinely collaborated with in the work of trying to repair what European settlement destroyed. This is not charity or sentimentality. It is recognition of the most basic practical fact about the situation. The people who managed this landscape sustainably for 60,000 years may have something important to teach the people who destroyed significant portions of it in 150, number 13, the rainfall records and what they are measuring. The long-term rainfall records for the Australian interior, now extending back more than a century for many stations, tell a complicated story. The complexity is partly methodological because the quality and coverage of weather observations varied enormously in the 19th and early 20th centuries, And partly climatic because Australia's rainfall is highly variable and driven by large-scale climate patterns, including El Nino and La Nina cycles that produce multi-year swings in precipitation independent of any human influence. But within that complexity, there are trends that are difficult to explain without reference to land use change. The reduction in average annual rainfall in the interior of Western Australia since European settlement and the associated land clearing is one of the most discussed and most controversial of these trends. The relationship between tree cover and rainfall is not simple, and the precise magnitude of the land use contribution to rainfall decline relative to climate variability and long-term climate change is still debated, but the direction of the relationship is not seriously in doubt. Removing trees reduces transpiration. Reducing transpiration reduces the moisture available in the lower atmosphere. Reducing available atmospheric moisture reduces the frequency and amount of convective rainfall. The salinity crisis of the Western Australian wheat belt, discussed earlier, also has a hydrological implication for rainfall. The removal of deep-rooted native vegetation reduced the amount of water being drawn from depth by transpiration. That water accumulated in the water table rather than being recycled to the atmosphere. In terms of the water cycle, clearing converted land that was participating actively in the regional water cycle into land that was much less active. The rainfall that fell on cleared land was more likely to run off or accumulate underground than to be recycled through vegetation back into the atmosphere. Whether this change in the water cycle's terrestrial component has measurably reduced rainfall over the wheat belt is a question that continues to be studied. The evidence is suggestive but not definitive because the confounding variables, particularly the multi-decade rainfall variability driven by ocean temperature patterns, make it difficult to isolate the land use signal with confidence. But the physics of the relationship are clear. Clearing native vegetation changes the way the landscape participates in the water cycle. It is not a neutral act in terms of regional hydrology. What is clear from the rainfall records is that many parts of the Australian interior that carry degraded vegetation are in a drier condition than they would be under intact native vegetation cover. Not only because of reduced transpiration, but because degraded land surfaces have different albedo characteristics than vegetated land. Bare ground reflects more solar energy and heats more rapidly than vegetated ground. The major dust storms that swept the eastern Australian interior during drought years from the 1940s through the present are visible in the historical record as periods of significantly reduced solar radiation at affected stations. The volume of soil being transported by those storms was an order of magnitude larger than anything recorded in the region's geological history of the Holocene. The storms were not a natural phenomenon. They were the visible manifestation of topsoil loss from degraded pastoral land. The continent's fertility literally blowing away in clouds visible from space. Number 14, the seeds that remember. One of the most remarkable facts about the degraded landscapes of the Australian interior is that the soil seed bank, the store of viable seeds buried in the upper layers of the soil, can remain partially intact even after decades of degradation. Seeds of native perennial grasses and forbs that have not been seen as living plants for decades can remain dormant in the soil, waiting for conditions that will allow them to germinate. This is both good news and bad news. The good news is that the potential for recovery is not zero, even in severely degraded landscapes, because the genetic material needed for that recovery has not always been completely lost. The bad news is that the conditions required for those seeds to germinate and establish are conditions that the degraded landscape cannot provide without active intervention to create them. The seeds of native Australian perennial grasses require specific conditions to germinate. They require the right combination of temperature and moisture. They require a surface that is not compacted to the point of preventing root penetration. They require freedom from competition from the dense mat of introduced annual weeds that now covers much of the degraded pastoral zone. And in many cases, they require fire, either actual fire or the application of smoke or smoke water, to break seed dormancy. Restoration ecologists working in the Australian interior have developed techniques for meeting some of these requirements in degraded landscapes. Careful application of fire under appropriate conditions can clear the introduced weed mat that prevents native plant germination. The exclusion of grazing from degraded areas for extended periods, years to decades, can allow soil structure to recover to the point where plant roots can penetrate. The direct seeding of native perennial grasses, using locally sourced seed wherever possible to maintain genetic diversity, can supplement the seed bank where that bank has been depleted below the threshold needed for natural recovery. These techniques work. There are restoration projects across the Australian interior that demonstrate measurable recovery of native plant communities in areas where that recovery was not considered possible a generation ago. The restoration work in the Western Australian wheat belt, the grassland restoration projects of the Australian Capital Territory, the work of the Australian Wildlife Conservancy in building fenced havens for native mammals. These are examples of what is possible when the right knowledge and the right resources are applied to landscapes that still contain this biological potential for recovery. What they also demonstrate is the scale of the challenge. The degraded area of the Australian interior is not the size of a nature reserve or a national park. It is continental. The area of degraded pastoral land alone covers millions of square kilometers. The area of agricultural land from which native vegetation has been cleared covers millions more. The restoration of anything approaching the functional native ecosystem that covered this land before European settlement would require resources, time, and political will that have not yet been assembled. But the seed banks in the soil are still there in many places. The knowledge is still there in the minds of Aboriginal elders who remember what the country looked like and how it worked. The ecological science is advancing rapidly. The direction of restoration is becoming clearer. The task is possible. It is just not yet being approached at anything like the scale it would require. Number 15. The animals that rewilded themselves. There is a counterpoint to the story of ecological collapse in the Australian interior, and it is worth telling because it offers genuine hope rather than false comfort. In the places where human management has been restored, either through the return of Aboriginal land management or through conservation interventions that mimic its effects, the landscape has shown a remarkable capacity for recovery. The return of the bilby to areas from which it had been absent for decades demonstrates something important about the resilience of ecosystems when the pressures that degraded them are removed. The bilby is not simply a distinctive Australian animal. It is a soil engineer whose burrowing activity has measurable positive effects on soil structure, water infiltration, and seed burial within years of its reintroduction. Areas where bilbies have been reintroduced show increased native plant diversity, improved soil porosity, and greater capacity to recover from drought compared to ungrazed areas without bilbies. The animal's doing work. Its return is not just aesthetic, it is functional. The rewilding of areas within fence conservation havens across the Australian interior is demonstrating that the native mammal fauna of the pre-European continent was not a collection of ecological passengers. It was a community of ecological engineers whose activities maintained the landscape in ways that made it more productive, more resilient, and more capable of supporting the full range of species that evolved in it. Remove the engineers and the landscape degrades. Return them and it begins to recover. The recovery is not instantaneous. It takes time, it takes scale, it takes the reconnection of processes that have been interrupted for decades or centuries. A landscape cannot recover its full ecological function from a single generation of protection. The soil biology takes decades to rebuild. The plant communities take decades to return to their pre-degradation composition. The mycorrhizal networks take decades to reestablish. But the direction of recovery is clear in the areas where it is being pursued, and the rate of recovery in Australian conditions is faster than many scientists had expected. The lessons being learned in Australian rewilding projects have relevance for Canada and for every country grappling with degraded ecosystems. The restoration of predator communities, particularly the ongoing debates about the reintroduction of wolves and cougars to areas from which they have been removed, mirrors the Australian debates about the role of apex predators in maintaining ecological function. The reintroduction of beaver to areas where they have been eliminated, and the recognition of beaver as keystone ecosystem engineers whose activity creates wetland habitat and regulates water flow, is another example of the same principle. Animals are not incidental to landscapes. They are constitutive of them. Remove them, and the landscape changes. Return them, and it changes back. Number 16. The political economy of landscape destruction. Why did the destruction of the Australian interior happen so rapidly and so completely? The ecological consequences were visible to observant people within decades of pastoral expansion. The warnings were there. The knowledge that land was being degraded was available. And yet the destruction continued and in many respects is continuing still. The answer is political economy. The destruction of the Australian interior was profitable in the short term, and its costs were externalized to the future and to the dispossessed. The pastoralists who overstocked their runs made money from the sheep and cattle they ran. The costs of the land degradation their overstocking caused were borne by the land itself, which could not present an invoice, by the Aboriginal people who were removed from it, who had no political voice to object, and by future generations who inherited the degraded landscape. This is not a specifically Australian phenomenon. It is the standard operation of extractive capitalism applied to land. The same logic that depleted the soil fertility of the American Great Plains in the Dust Bowl era, that stripped the topsoil from China's Loess Plateau, that logged the old-growth forests of the Pacific Northwest to the edge of ecological function, operated in the Australian interior. The resources were there. The technology to extract them was available. The institutional framework that might have imposed constraints on extraction in the interest of long-term sustainability did not exist or was not applied. The extraction proceeded until it hit the ecological limits of the landscape. In Australia, as in other colonial contexts, The removal of the indigenous population from the land was a precondition for this extraction. The Aboriginal people who had managed the Australian interior were not just users of the land, they were its managers. Their presence on the land was itself a form of management, and their removal was the removal of that management system. The dispossession of Aboriginal Australians was not only a moral catastrophe, it was an ecological one. The land rights movement in Australia, which from the 1970s onward began the slow and contested process of returning legal title over some portions of Australia to Aboriginal communities, is therefore not just a matter of justice in the abstract. It is a matter of ecological management. The areas of Australia where Aboriginal land management has been most successfully restored, primarily in Northern Australia and in some parts of the centre, are the areas showing the most positive ecological trends. The return of land to Aboriginal custodians is correlated with the return of ecological health to that land in ways that are increasingly documented in the scientific literature. This correlation is not coincidence, it is causation. The indigenous custodians who return to their country bring with them the knowledge systems that maintain that country for thousands of years. They apply those knowledge systems, adapting them to change conditions but maintaining their fundamental logic. The country responds. It always does, when given the chance. Number 17. The dust that tells the story. The dust storms of the Australian interior are one of the most dramatic and most underappreciated environmental phenomena in the country. In the popular imagination, they are weather events, things that happen like cyclones or floods, outside the category of human-caused phenomena. They are red and vast and occasionally spectacular enough to make international news, and then they are forgotten until the next one. But dust storms are not weather. They are symptoms. They are the landscape's most legible communication about its own condition. A landscape with intact native vegetation cover does not generate large dust storms in the way that degraded landscapes do. The dust that rises in the storms and travels hundreds or thousands of kilometers before settling in the ocean or on the eastern seaboard is topsoil. It is the physical substance of the continent's fertility being removed from the interior and deposited somewhere it cannot be used. The dust storms of the Australian interior have been documented with increasing scientific rigour over the past several decades. Researchers monitoring the composition of dust collected during storm events have found that it is not just mineral particles. It contains significant quantities of nutrients, including phosphorus and nitrogen, that are essential for plant growth. The offshore deposition of this dust into the Tasman Sea and the Southern Ocean has been shown to contribute measurably to marine productivity in those waters. The Australian continent is fertilizing the ocean with its own topsoil, a process that is neither natural nor desirable, and that represents a net loss of productive capacity from the land that will not be replaced on any human timescale. The volume of material moved in major dust storm events is staggering. The 2009 dust storm that turned Sydney orange and deposited an estimated 5 million tonnes of topsoil into the Tasman Sea in a single event drew its material primarily from the degraded pastoral lands of Western New South Wales and Queensland. The event was dramatic enough to generate significant media attention, but it was not an unusual event in the history of the Australian interior. It was a large example of a pattern that has been occurring at varying scales since the pastoral era destroyed the vegetation cover that held the soil in place. The monitoring of dust storm events over time shows that the frequency and intensity of large storms correlates with drought and land condition. During wet periods, when vegetation cover is temporarily improved, dust storm activity decreases. During droughts, when vegetation fails on already degraded land, dust storm activity increases dramatically. The underlying driver of the storms is not the drought itself. Droughts have always occurred in the Australian interior. The underlying driver is the vulnerability of the degraded landscape to dust generation under drought conditions, a vulnerability that would not exist if the perennial native vegetation that holds the soil under drought conditions had not been removed. The dust tells the story of the desert's creation in the most direct possible way. It is the desert in motion. It is the past of the landscape, the accumulated soil and biological material of thousands of years of productive ecosystem function, being moved by the wind to places where it will be lost forever from the land that produced it. Number 18, the language that carried the landscape. Among the Aboriginal language groups whose territories covered the Australian interior, words existed for ecological conditions, landscape features, and biological relationships that have no equivalents in English. The loss of those words, as languages were suppressed and their speakers killed or displaced, was not merely a cultural tragedy, it was an ecological one. A language encodes the observations of the people who developed it. A language with specific words for the different stages of spinifex grass growth, for the specific sound that a particular creek makes in different water conditions, for the precise combination of plant species that indicates a particular water source is nearby, is a language that contains specific and accurate ecological information. When that language is lost, the information it encoded becomes inaccessible, not because it was wrong, but because the categories it used to organize observation are no longer available to the minds of people who need to understand the landscape. The concept of country in Aboriginal Australian thought is not translatable into English without significant loss. Country is not land in the sense of a physical surface with property boundaries. Country is a living relationship between a people and a place, encoded in language, ceremony, story, and practice, that contains within it everything that people and place have learned about each other over thousands of years. The specific obligations that flow from a person's relationship with their country, including the obligations of land management, the responsibility to perform the ceremonies that maintain the country's health, the duty to teach the next generation the knowledge that the country requires of its custodians, are not transferable outside the language and cultural context in which they developed. The revival of Aboriginal languages, now supported by a growing number of language reclamation programs across the country, is not only a matter of cultural heritage, it is a form of ecological restoration. Languages carry ecological knowledge. Reviving the language begins the process of reviving the knowledge system it encoded. And that knowledge system, as we have seen throughout this script, is not academic or historical, it is practical. It is the operating system that the Australian landscape evolved with. It has applications in the present that the people reviving it are beginning to discover. The relationship between language and landscape in Aboriginal Australia is among the most intimate of any documented in the world. The land is named in the language. The language describes the land. The songs that encode navigational knowledge, the stories that preserve ecological information, the ceremonies that maintain the human relationship with specific plants, animals, and landscape features, all of them are conducted in the language of the country they belong to. The language and the country are not separate things that happen to be associated. They are aspects of the same relationship. Number 19, the ocean that receives the continent. The coral reefs of the Great Barrier Reef and the coastal waters of southern and western Australia have received something from the degraded Australian interior that they did not ask for and cannot easily absorb. The rivers that drain the degraded pastoral and agricultural lands of the interior carry to the coast the dissolved products of that degradation: nutrients, sediments, agricultural chemicals, and salt. The Great Barrier Reef, one of the largest living structures in the world and the most biodiverse marine ecosystem in Australian waters, is particularly vulnerable to the nutrient and sediment inputs from the rivers that flow through the sugar cane and cattle country of coastal Queensland. Elevated nutrient levels promote the growth of algae that compete with coral for space on the reef. Elevated sediment reduces the light availability that coral requires for its symbiotic photosynthetic organisms. The combination of nutrient enrichment and sediment stress makes reefs more vulnerable to the bleaching events caused by elevated ocean temperatures and makes their recovery from those events slower. The relationship between inland land use and reef health is one of the most direct demonstrations available of the way in which landscape degradation does not stay in the degraded landscape. It moves. It moves through the waterways. It moves through the atmosphere as dust. It moves through the ocean currents that carry it to ecosystems that have no way to reject it. The desert that is being created in the interior of Australia is not just an interior problem. It is an ocean problem. The sediment delivered by Queensland rivers to the Great Barrier Reef has increased by an estimated 8-fold since European settlement compared to pre-European levels. This increase is the direct result of the land clearing and grazing practices that strip the vegetation from the catchments of those rivers. The clearing reduced the landscape's capacity to intercept and retain sediment. The grazing compacted the soil and reduced infiltration, increasing runoff. The result was rivers carrying many times more sediment to the reef than they did before the land in their catchments was changed. The reef does not have the capacity to adapt to this rate of change. Reefs are slow-growing structures that took thousands of years to build. The degradation of water quality that has occurred in the last 150 years is happening faster than coral communities can respond. The parts of the reef closest to the coast and most exposed to river plumes are showing measurable decline in coral cover and diversity compared to historical baselines. This decline is not primarily the result of climate change. It is the result of catchment degradation that was completed in the 19th and early 20th centuries, whose consequences are still arriving at the reef with each flood event and each delivery of sediment from the degraded pastoral lands upstream. Number 20, the forests that fed the rain. The relationship between Australia's forests and its interior drylands is more intimate and more consequential than it appears on a map. The forests of the Great Dividing Range and the coastal highlands are not simply adjacent to the interior. They participate in creating the conditions under which rainfall reaches the interior, moderate the temperatures of the air masses that move across the continent, and maintain the river systems that flow from them into the interior. The clearing of these forests, which proceeded along the Australian eastern seaboard throughout the 19th and 20th centuries, with a thoroughness that has left only fragments of the original forest cover in most regions, changed the hydrology of the entire eastern river system. The rivers that originate in the ranges are smaller and more variable than they were before clearing, because the vegetation that intercepted rainfall released it slowly through the season and contributed transpiration to the regional water cycle has been replaced by agricultural land that handles water very differently. The old-growth forests of the Victorian and New South Wales highlands are among the most water-productive ecosystems in Australia. Their root systems reach deep into the bedrock. Their canopies intercept rainfall and distribute it through the soil rather than allowing it to run off the surface. Their transpiration contributes significantly to the moisture available for convective rainfall in the ranges themselves and in the lee of the ranges. Remove them and the rivers run faster in flood and slower in drought. The catchment becomes less reliable, delivering more water during peak events and less during low flow periods, exactly the pattern that makes water management more difficult and less beneficial for the ecosystems downstream. The recognition that old growth forests produce more reliable water yields than logged forests is now established in the scientific literature for Australian conditions. Studies comparing the hydrology of logged and unlogged catchments have consistently found that logged catchments produce less water in low flow periods because the regrowth forest that follows logging has a higher water demand than the mature forest it replaces, due to the rapid growth of young trees requiring large quantities of water for metabolic activity. The logged catchment is a less efficient water catchment in the periods when water is most needed, the dry periods following drought. This finding has significant implications for the management of water supply catchments, most of which in southeastern Australia contain significant areas of state forest available for logging. It implies that the logging of water supply catchments is a direct economic and ecological cost that has been treated as an external benefit, timber revenue, without accounting for the cost of the water yield reduction that logging produces. The accounting has been systematically incomplete. The forests that were cleared in the 19th and 20th centuries, both in the ranges and on the plains, are mostly gone and cannot be simply regrown even where the political will to do so exists. Forest restoration requires decades of protection and active management to produce ecosystems even approximating as a function of the original forest. But in some areas, particularly where remnant patches of native vegetation provide the seed source and fungal inoculum for recovery, forest restoration is happening and producing measurable results within years to decades. The speed and success of restoration is proportional to the quality of the starting conditions, which means that protecting the remnant vegetation that remains is the single most important thing that can be done to preserve the option of future restoration in areas where the vegetation has not yet been completely removed. Number 21. The plants that built the soil. Among the most misunderstood aspects of the Australian interior's ecological history is the role that native plants played not just in occupying the soil, but in creating it. The notion that soil is a physical substrate within which plants grow is a fundamental misunderstanding of the relationship between soil and vegetation in Australian conditions. Australian soils, particularly in the arid and semi-arid interior, were built by vegetation as much as they were occupied by it. The process by which native perennial grasses contributed to Australian desert soil formation over thousands of years is one of the most important stories in Australian ecology, and it is almost entirely invisible to the casual observer. The key actors are the root systems of perennial grasses, the soil organisms that depend on those root systems, and the slow accumulation of organic matter that those organisms process into the nutrient-rich upper soil layers that support productive plant communities. The root systems of native perennial grasses can penetrate to depths of several meters in the sandy desert soils of the Australian interior. As these roots grow, they create channels through the soil that improve drainage and aeration. As the roots die and decompose, they add organic matter to the soil at depth, enriching the soil profile in ways that improve its water holding capacity and its nutrient availability. Over thousands of years, this process of root growth and decomposition builds a soil profile that is significantly more fertile and more functional than the mineral substrate below it. When perennial grasses are removed by overgrazing, this process stops. The channels created by the old root systems gradually close as the soil compacts. The organic matter that was being added by root decomposition is no longer being replenished. The soil organisms that process that organic matter decline as their food source diminishes. The soil profile begins to simplify, losing the complexity and fertility that took thousands of years to develop. The recovery of this soil building process when perennial grasses are re-established is possible, but it is slow. The rates of organic matter accumulation in desert soils are measured in decades. The recovery of the full soil biological community that sustains perennial grass growth requires the recovery of both the plant community and the animal community that interacts with it, including the burrowing mammals that aerate the soil, the termites that decompose organic matter, and the ground-dwelling insects that maintain the nutrient cycle. Each component of the community depends on the others, and all of them take time to recover once they have been disrupted. The patience required for soil recovery in the Australian desert is patience measured in generations. This is one of the most difficult facts to convey to a political system that operates in 4-year cycles and an economic system that demands returns on investment within years. The restoration of degraded Australian soils is possible. It is happening in some places, but it will not produce results that are politically or economically legible within the timeframes that the systems making decisions about land use are designed to operate in. The soil does not care about election cycles. Number 22, the water that was promised. When British settlers began moving into the Murray-Darling Basin in the first half of the 19th century, they encountered a river system that looked, to eyes trained on European rivers, like an invitation. The water was there, the land was flat and fertile, the climate was warm and sunny. What was needed was irrigation, the technology that had made the Fertile Crescent fertile, the Nile Valley productive, the rice paddies of Asia rich. Apply water to good soil in a warm climate and you get agriculture. It seemed obvious. The Murray-Darling Irrigation Commission and its successors proceeded on this basis. They built dams, they built canals, they built weirs. They allocated water to irrigators in quantities that reflected the river's average flow rather than the range of flows it experienced. They did not adequately account for the fact that Australian rivers are not like European rivers. They are not reliably fed by consistent rainfall or glacial melt. They are driven by the most variable rainfall of any comparable river system on Earth, with flows varying by orders of magnitude between flood years and drought years. The allocations they made were therefore optimistic in a structural way. They reflected what the river could provide in average years. They did not reflect what it could provide in the drought years that would inevitably come, and that in the Australian climate come frequently. When the droughts arrived, as they always did, the water that had been promised to irrigators was simply not there. The response was not to reduce allocations to a level the river could reliably sustain. It was to build more storage, to extract water more efficiently, to defer the reckoning by making the system more capable of moving water during wet periods, to compensate for what would not be available in dry ones. The reckoning eventually arrived in the early 21st century in the form of the Millennium Drought that lasted from approximately 1997 to 2009, and that demonstrated with brutal clarity that the Murray-Darling system had been over-allocated by a factor that the existing governance structure was not designed to address. The river did not reach the sea consistently during this period. The lower lakes turned acidic as the sulfide soils that had been submerged for centuries were exposed to the air by the falling water level. The communities of wetland plants and animals that depended on the river's flow experienced catastrophic decline. The political response to the Millennium Drought produced the Murray-Darling Basin Plan, a landmark piece of water governance legislation that for the first time attempted to define the environmental water requirements of the river system and to return sufficient water from agricultural extraction to meet those requirements. The plan was politically contested, scientifically debated, and implementationally imperfect, but it represented an acknowledgement, unprecedented in Australian water governance, that the river system itself had legitimate water needs that had to be met before irrigators' demands were fully satisfied. The history of the Murray-Darling is the history of a promise that could not be kept, a promise of irrigation wealth made to settlers who took up land in good faith based on the assumption that the river would always provide what the good years suggested it could provide. It was a promise made without understanding the river system that was being promised. And the fulfillment of that promise to the maximum extent that the river's actual capacity allowed came at a cost to the river itself that has still not been fully reckoned with. Number 23, the salt that rose from below. There is a form of landscape death that is uniquely Australian in its scale and its mechanism, though it is not unique in its cause. Dryland salinity is what happens when you remove the trees from a continent that spent millions of years accumulating deep stores of salt in its geology, and that relied on deep-rooted vegetation to keep that salt safely below the surface. Australia is an old continent. Its soils have been leached by rain for millions of years, and the salts that rain dissolves from rock and soil have accumulated over geological time in the deeper layers of the landscape. Under native vegetation, particularly under the deep-rooted woodland species that covered much of southern Australia before European settlement, these salt stores were held in place. The roots of the native trees drew water down from the surface to depths of many meters, keeping the water table below the level at which the salt could be mobilized upward. The salt stayed underground. The plants grew undisturbed in the freshwater zone above it. Clear the native trees, and the situation changes immediately. Without the deep-rooted vegetation drawing water from the soil, rainfall that previously would have been absorbed and transpired by the trees begins to accumulate in the water table. the water table rises. As it rises, it approaches the salt-bearing layers. When it reaches them, it begins to dissolve and carry the salt upward. When the salt-bearing water reaches close enough to the surface for evaporation to concentrate it, it crystallizes on or near the soil surface. The result is a landscape whitened with salt crystals, a soil so toxic that almost nothing will grow in it. A stretch of land that was farmable when it was cleared, and that has been rendered permanently unproductive by the clearing itself. The scale of dryland salinity in Australia is almost incomprehensible. Millions of hectares of agricultural land in the wheat belt of Western Australia alone are affected or at risk of being affected. The annual economic cost of production losses and infrastructure damage from dryland salinity has been estimated in the billions of dollars. The ecological cost, measured in the loss of remnant native vegetation communities, waterway health, and biodiversity, is incalculable in any straightforward economic sense. The process cannot be reversed by simply replanting native vegetation, because by the time salinity becomes visible at the surface, the water table has already risen to the point where the salt cannot be returned to its original position without decades to centuries of consistent deep-rooted transpiration. Revegetation is necessary for recovery, but it is the beginning of a very long process rather than a straightforward remedy. In the most severely affected areas, the damage may not be reversible within any planning horizon that current society is prepared to work with. This is perhaps the clearest example in the entire Australian story of how colonial land use created problems that operate on geological timescales. The salt that is rising to the surface of the Western Australian wheat belt has been accumulating in the landscape for millions of years. It was held in place for thousands of years by the vegetation that Indigenous Australians managed and that European settlers cleared in a matter of decades. Its consequences will continue to unfold for centuries regardless of what actions are now taken. The clearing was fast, the healing will be slow. Number 24, what burned and what remained. The 2019 and 2020 Australian bushfire season, known internationally as the Black Summer, burned approximately 18 to 19 million hectares of southeastern Australia in a period of months. It was the largest fire event in Australian recorded history in terms of area burned, and it killed or displaced an estimated 3 billion animals. The smoke from the fires was visible from space and traveled around the world. The fires were described almost universally, both in Australia and internationally, as a climate disaster. Climate change was certainly a contributing factor. The conditions that made the fires possible, extreme heat, low humidity, strong winds, and drought, were intensified by the warming that climate change has produced and is continuing to produce in Australian conditions. But the fires were not only a climate disaster, they were also an ecological disaster that had been building for generations, the consequence of the same disruption of fire management regimes that has driven the degradation of the Australian interior, described throughout this script. The forests that burned in the Black Summer fires had not been regularly managed by cultural burning for most of the preceding century and a half. The fuel loads that had accumulated in the absence of regular, low-intensity burning were enormous, far larger than they would have been under traditional management. When the fire came, under the extreme conditions of the drought and the heat, it had more fuel to burn than any previous fire in the historical record. And it burned with a ferocity that reflected not just the climate conditions of that particular season, But the century and a half of fuel accumulation that those climate conditions ignited, in the aftermath of the Black Summer fires, there was an unprecedented level of public and scientific discussion about the relationship between traditional burning practices and catastrophic fire risk. Aboriginal and Torres Strait Islander land managers and cultural burning practitioners, some of whom had been attempting to reintroduce traditional burning practices for decades in the face of institutional resistance, found themselves in sudden demand as consultants, partners, and experts in a way they hadn't previously experienced. The knowledge that had been dismissed or ignored for generations was, in the wake of the most catastrophic fire season in recorded history, suddenly being recognized as potentially essential. This recognition is genuine and it represents real progress. But it also carries a weight of irony that is difficult to set aside. The knowledge was always there. The practitioners were always available. The evidence that traditional burning reduced catastrophic fire risk was already present in the landscapes where it was being practiced. What changed was not the knowledge. What changed was the catastrophe that made ignoring the knowledge no longer politically viable. The recovery of the forests burned in the Black Summer fires is ongoing. Many areas are showing the regenerative capacity that characterizes fire-adapted Australian vegetation, with seeds germinating and epicormic growth erupting from the burned stems of eucalypts, with the speed that reflects a relationship between plant and fire refined over millions of years. But the recovery will take decades. The wildlife populations that were devastated will take generations to rebuild, if they rebuild at all. And the climate trajectory that made the fires as severe as they were has not been reversed. Number 25, what the desert is asking. We return at the end to the beginning. The Australian desert is not natural. It is what remains after something was cut down, grazed out, burned wrong, flooded with salt, silted into rivers, and blown into the ocean. It is the consequence of a century and a half of land management practices that did not understand the land they were managing and that systematically destroyed the knowledge systems of the people who did. The desert is asking, in the way that only landscapes can ask, whether the people who created it are ready to understand what was lost and to commit to the work of restoring it. It is asking this question with the evidence of its own condition, with the dust storms that carry its fertility to the sea, with the rivers that no longer run clear, with the soil that will not hold rain, with the animals that are gone from the places where they should be, with the silence in landscapes that should be loud with life. The question has an answer that begins not with technology or policy, though both are needed, but with knowledge. With the knowledge held by the Aboriginal Australians who managed this continent for 60,000 years, and who maintain that knowledge imperfectly in conditions that have made its maintenance extraordinarily difficult, but that have not extinguished it. With the knowledge being developed by the scientists and ecologists who are beginning to understand with rigor and humility what the pre-European landscape was and what it needs to become functional again, with the knowledge accumulated by the land managers, some Aboriginal, some not, who are already doing the work of restoration on the ground in the degraded landscapes of the real Australian interior, and who are seeing results that prove the work is worth doing. The desert that was made can, to some extent, be unmade. The process will be slow, it will be expensive, it will require changes in the political economy of land use in Australia that have not yet been achieved and that will face sustained resistance from interests that profit from the current arrangements. But it is possible. The land remembers what it was. The knowledge of how to help it return exists. The question is whether the will to use that knowledge in time to matter can be assembled. That is not a question the land can answer. It is a question for the people who live on it. And it is a question that matters not only for Australia, but for every country that has ever replaced the management of a landscape with the extraction of it. The lesson that the Australian desert teaches is universal. Landscapes are not resources, they are relationships, and relationships, once broken, require patience, effort, and humility to repair. Sleep well tonight, and tomorrow look at every landscape around you and ask what story it is trying to tell. Ask what was there before. Ask who managed it and how. Ask what was lost. Because the land is always speaking. The only question has always been whether we are willing to stop long enough to hear it. Number 26. The termites and the invisible engineers. Beneath the red soil of the Australian interior, in the spaces between the roots and the rock, there is an engineering core that most people never think about, and that virtually no one was thinking about when European settlement began transforming the landscape. The termites of the Australian desert are among the most important ecosystem engineers in one of the harshest environments on Earth. And the story of what they do and what happens when their work is disrupted is a story about complexity that cannot be seen but cannot be ignored. Australia has more species of termites than almost any other country on Earth. More than 300 species have been described, and the diversity of their ecological roles is as wide as the diversity of their forms. Some termites build the great mound structures that are landmarks of the northern Australian landscape. Others live entirely underground, invisible to anyone walking above them. Some eat wood, some eat grass, some eat soil itself, processing the mineral material and the organic residues within it in ways that change the soil chemistry available to the plants above them. The termites of the desert interior are the continent's primary decomposers of dead plant material. In the absence of the moisture that drives fungal decomposition in wetter climates, termites take on the role that fungi play in tropical forests, breaking down dead vegetation and returning its nutrient content to the soil in forms that plants can absorb. A landscape without active termite communities is a landscape where dead vegetation accumulates rather than decomposing, where nutrients remain locked in plant matter rather than cycling back through the soil, where the foundations of soil fertility are compromised. European settlement did not primarily target termites. It targeted vegetation, and it compacted soil, and it introduced hooved animals whose trampling transformed the physical environment that termites lived in. The disruption of termite communities was therefore a secondary consequence of processes aimed at other things, which made it almost entirely invisible as a cause of landscape degradation. But the correlation between the loss of diverse termite communities and the reduction of soil fertility in heavily grazed Australian rangelands is real, and it is documented. The recovery of termite diversity in restored or rested landscapes is one of the earliest and most reliable indicators that soil rehabilitation is progressing. When soil compaction is reduced by the removal of livestock, when organic matter begins to accumulate again at the surface, when the moisture regime in the soil begins to stabilize, the termites return before most other indicators of recovery are measurable. They are the first signal that the invisible foundation of the landscape is beginning to function again. Number 27. The plants that should not be there. Across millions of hectares of the Australian interior, the dominant plants are not Australian. They are African, they are European, they are South American, they are plants that arrived in the holds of ships, on the wool of sheep, in the seed mixes that pastoral companies seeded onto degraded land in the vain hope that something, anything, would grow and hold the soil in place. They are plants that had no prior relationship with Australian soil, Australian fire, Australian animals, or Australian climate, and that consequently behave in ways that Australian ecosystems have no evolved response to. Buffel grass, already mentioned in the context of its impacts in northern Australia, is perhaps the most significant of these alien landscape transformers in the arid zone. Its spread across central Australia over the past half century has converted areas of complex native spinifex grassland, rich with the specific animal communities that evolved with spinifex, into simplified buffel monocultures. The change in fire behavior that accompanies this conversion, hotter, faster, more intense fires that kill the mature mulga and acacia trees that survive traditional burning, is creating a landscape that looks increasingly like a simplified, impoverished version of its former self. Prickly pear cactus, introduced to Australia in the early 19th century as a food source for the cochineal insects used in dye production, colonized approximately 26 million hectares of Queensland and New South Wales by the 1920s, rendering much of it impenetrable to agriculture or grazing. The biological control that eventually reduced prickly pear populations, the moth Cactoblastis cactorum, is a famous and genuinely successful example of biological pest control. But the landscape that prickly pear left behind after it was controlled was not the landscape that had existed before it arrived. The native plant communities that prickly pear had displaced did not simply resume their former occupancy when the cactus was removed. Other opportunistic species moved in. The recovery of native vegetation was partial and uneven. Introduced pasture grasses planted deliberately across tens of millions of hectares of northern and central Australia to improve the carrying capacity of cattle stations, have spread far beyond the areas they were seeded and have colonized native plant communities that were never targeted for replacement. The grasses that have spread most successfully are those that are most competitive under the conditions of degraded Australian rangelands, which means they are the least likely to support the native animal communities that evolved with the original vegetation. A paddock covered in introduced buffel or introduced African lovegrass supports a fraction of the native animal diversity that the same paddock covered in native spinifex or Mitchell grass would have supported, because the food resources, shelter structures, and habitat complexity that native animals evolved to exploit are not present in the simplified introduced vegetation. The introduced plant problem is one of the most difficult aspects of the Australian landscape crisis to address, because introduced plants that have established across continental scales cannot be removed by any practical means. Biological control, herbicide application, and manual removal are tools that work at local scale but that cannot be applied across the millions of hectares where introduced grasses have established. The long-term management of introduced vegetation in Australian rangelands will require a combination of approaches that has not yet been fully developed, and it will require sustained investment of resources and institutional commitment over timescales that exceed those of any current policy horizon. Number 28. The country that was mapped from ignorance. The maps that European explorers produced of the Australian interior in the 19th century were exercises in determined misunderstanding, not because the explorers were incompetent, although some of them made mistakes that their more careful colleagues documented with exasperation. The misunderstanding was structural. It was built into the categories that the maps used and the assumptions that those categories encoded about what a landscape was and how it should be described. European cartography in the 19th century was a technology of resource identification and territorial claim. A map recorded what was there and in whose possession it was. Water was recorded as a fixed feature, a river, a lake, a permanent waterhole. Vegetation was recorded in broad categories that reflected the potential agricultural or pastoral use of the land. The land itself was divided into parcels that could be allocated, leased, and owned in the European legal sense. None of these categories adequately described the Australian interior. Water in the Australian interior is not a fixed feature. It is a dynamic system in which the same location may be a river in a wet year and a dry channel in a drought year, and in which the concept of a permanent water source is relative to a variability that spans decades. Vegetation in the Australian interior is not a stable background against which human activities take place. It is a dynamic community that responds to rainfall variation, fire, grazing, and the complex interactions between all of these, with changes that operate on timescales ranging from seasons to centuries. The land is not a simple surface that can be parceled out without reference to the living systems that make it functional or dysfunctional. The maps that allocated the Australian interior to pastoral leases and agricultural selections in the 19th century were therefore maps of a landscape that had been fundamentally misrepresented. They showed potential that was real but conditional, conditional on management practices that the landscape could sustain, conditional on understanding the variability that the climate would deliver, conditional on maintaining the biological systems that made productivity possible. The allocation documents that accompanied the maps assigned those conditional resources as if they were unconditional. The land was leased for cattle or sheep at stocking rates calculated from the apparent carrying capacity of good years, without reference to the drought years that would inevitably arrive and that the landscape would need to survive. The consequence was that the pastoral allocation of the Australian interior was, from its beginning, an exercise in the systematic overestimation of what the landscape could support. Every drought exposed this overestimation. Every drought killed stock and compelled some reduction in numbers. And then the rains returned, and the optimism returned with them, and the numbers climbed again, and the land was pushed again to the limits of its capacity and beyond. The pattern repeated across the pastoral zone for a century and a half with a consistency that looks, in retrospect, like a collective inability to learn from experience. Number 29. The satellite that saw what the eye missed. The transformation of our understanding of the Australian interior in the last half-century owes more to satellite remote sensing than to any other single technology. The ability to observe vegetation cover, soil condition, fire scar patterns, and surface moisture across the entire continent with a consistency and frequency that no ground-based observation network could match has revealed things about the Australian landscape that were not visible before. The satellite record shows, among other things, that the area of bare or nearly bare ground in the Australian pastoral zone is significantly larger than contemporaneous ground level assessments suggested. Land managers assessing the condition of their runs by riding through them on horseback or by driving along stock routes and boundary tracks were systematically undersampling the condition of the landscape between the tracks. The satellite looks at everything simultaneously. The satellite record also shows the spatial and temporal patterns of vegetation recovery and decline with a clarity that allows the identification of the specific management practices and the specific rainfall events that drive change. Areas where grazing pressure is reduced show measurable increases in ground cover that are detectable from space within months of a significant rainfall event. Areas under continued heavy grazing show progressive decline in ground cover during dry periods and slower recovery during wet ones. The satellite is providing for the first time a complete and objective record of the relationship between land management practices and landscape condition across the entire continent. This record has been used to evaluate competing land management approaches with a rigor that was not previously possible. The comparison of vegetation cover trends in areas managed by Aboriginal communities using traditional burning practices with cover trends in adjacent areas managed by conventional pastoral or conservation approaches has provided some of the most compelling evidence available for the effectiveness of traditional management. The satellite does not care about cultural preconceptions or political convenience. It records what is there. The remote sensing technologies that have transformed our understanding of the Australian landscape also extend to subsurface features that were previously invisible. Ground-penetrating radar and other subsurface sensing technologies are beginning to reveal the architecture of the soil profile, the distribution of root systems, the location of saline groundwater, and other features that determine whether a given area of land is on a recovery trajectory or a degradation one. Combined with the long-term vegetation cover record from satellites, this subsurface information is creating a three-dimensional picture of landscape condition that is changing how restoration planning is conducted in the Australian interior. Number 30. The birds that fell silent. The birds of the Australian interior are among the best documented wildlife groups in the country. Not because ornithologists are more numerous than other kinds of naturalists, although they may be, but because birds are visible in ways that most other wildlife groups are not, and because the long tradition of bird watching in Australia has produced survey records extending back decades that allow the comparison of historical and current species occurrence. Those records tell a story that parallels, in the aerial dimension, the story of the mammal decline in the terrestrial one. Many species that were common across wide areas of the Australian interior in historical surveys are now absent from areas where they were previously regular. The decline of granivorous birds, seed-eating species that depended on the abundant seed production of the native perennial grasslands, tracks the destruction of those grasslands with a directness that leaves little room for alternative explanations. The grasses are gone, the seeds are gone, the birds are gone. The plains wanderer, a small cryptic bird that lives in native grasslands of the inland plains of southeastern Australia, is now critically endangered because the grasslands it requires have been reduced to a fraction of their former extent by cropping, grazing, and the invasion of introduced annual grasses. The grasslands that remain are mostly in private ownership, fragmented, and under continued pressure from the grazing and cropping that reduced them in the first place. The survival of the plains wanderer depends on maintaining the native perennial grasslands that remain, a task that requires active management by landowners and land managers who may or may not prioritize native grassland conservation over the agricultural productivity of the same land. The decline of woodland birds across the agricultural zone of southeastern Australia is one of the most thoroughly documented ecological changes in Australian conservation literature. The clearing of native woodland, the replacement of diverse native understory with introduced pasture grasses, the removal of dead trees and fallen logs that provided nesting hollows and invertebrate habitat, and the fragmentation of remaining native vegetation into patches too small to support viable populations. These are the processes that have silenced the woodland bird communities of the agricultural zone. The silence is not metaphorical. Surveys in agricultural landscapes that were covered in native woodland a century ago document bird communities that are a fraction of the diversity of those that existed in the intact woodland. The recovery of bird communities in restored areas provides some of the most emotionally legible evidence of what ecological restoration can achieve. When native vegetation is planted and allowed to grow for decades, when dead trees are left standing for hollow nesting species, when understory diversity is maintained, the birds return with a speed and enthusiasm that surprises observers who expected recovery to be slower. Species that had not been recorded in an area for decades appear within months of conditions becoming suitable. The birds are tracking the habitat, and the habitat, when it recovers, calls them back. Number 31. The economic reckoning that has not arrived. The degradation of the Australian interior has an economic cost that is partly measured and largely unmeasured. The measured portion is significant. The cost of managing the health consequences of dust storms on urban populations, the cost of repairing infrastructure damaged by erosion and flooding exacerbated by vegetation loss, the cost of water treatment for river systems carrying sediment and nutrient loads far above natural levels, the cost of production losses from degraded pastoral land, the cost of species recovery programs for animals pushed toward extinction by habitat loss. The unmeasured portion is much larger. It includes the loss of what ecologists call ecosystem services, the value of the functions that healthy ecosystems provide without charge to the humans who benefit from them. The water filtration provided by intact riparian vegetation, the flood moderation provided by native grassland root systems that absorb rainfall rather than allowing it to run off, the pollination services provided by native insects in remnant native vegetation adjacent to agricultural land, the carbon sequestration provided by intact native vegetation now absent from the tens of millions of hectares of cleared land that no longer stores the carbon that growing plants remove from the atmosphere. The economic framework within which Australian land use decisions are made does not include most of these values. A pastoralist who overstocks a run and degrades the land captures the economic benefit of the additional stock carried above the land's sustainable capacity, while the costs of that degradation in reduced future productivity, in downstream water quality impacts, in accelerated erosion, are borne by the landscape itself and by society at large. The private economic incentive and the public ecological interest are directly opposed, and without governance mechanisms that align them, the private interest tends to win. The development of economic instruments that internalize the cost of ecological degradation and the benefit of ecological restoration is one of the most important policy challenges in Australian environmental management. Carbon markets that pay for vegetation retained or replanted, payments for ecosystem services that compensate landowners for maintaining ecological functions that benefit the wider community. environmental water purchasing programs that acquire water rights for river health rather than agricultural use. These are all attempts to change the economic calculus of land use decisions in ways that favor ecological sustainability over short-term extraction. They are useful instruments. They are not sufficient at current scale. The area of Australian land in need of restoration is so large, and the economic value of current extractive use so embedded in the expectations of the people who hold those land use rights, that the economic transformation required to align private incentives with ecological sustainability represents a challenge as great as the ecological challenge itself. Number 32, the carbon the desert is releasing. The soils of the Australian interior contain carbon, not in the quantities that tropical soils or temperate agricultural soils contain, because Australian desert soils are poor by global standards of organic matter content. But the carbon they contain is not trivial, and its loss through the processes of degradation is not a trivial contribution to the global carbon budget. When perennial vegetation is removed from semi-arid land, the carbon stored in the root systems and the organic matter of the soil is released to the atmosphere through the respiration of soil organisms that decompose the dead organic matter. The rate of release depends on temperature, moisture, and the size of the carbon pool being depleted. But in Australian conditions, significant fractions of the soil carbon pool can be lost within years to decades of vegetation clearance or vegetation death through overgrazing. The clearance of native Australian vegetation for agriculture and pastoral use over the past century and a half has released very large quantities of carbon to the atmosphere. This release has been partially accounted for in national greenhouse gas inventories, but the accounting is incomplete because the soil carbon component of the loss is difficult to measure with precision and has historically been underestimated. The vegetation clearing component, representing the carbon in above ground biomass that was burned or decayed when the trees and shrubs were removed, is better measured but still uncertain in magnitude. The restoration of native vegetation on cleared Australian land offers the reverse of this process. The resequestration of carbon as growing vegetation accumulates biomass and as recovering soil biology begins to rebuild the soil organic matter pool. This potential has driven significant interest in vegetation restoration as a carbon offset mechanism, and several large-scale restoration projects in Australia are now operating at least partly on the basis of carbon credit revenue. The climate mitigation potential of restoring degraded Australian landscapes is not trivial. Estimates of the carbon that could be sequestered by restoring native vegetation across the degraded pastoral zone and agricultural zone of Australia run to billions of tons over decades. This is not a substitute for the reduction of fossil fuel emissions, which remains the primary requirement for meaningful climate mitigation, but it is a real and potentially very significant contribution to the national carbon budget, and one that delivers ecological co-benefits that go far beyond the climate value alone. The intersection of climate mitigation, ecological restoration, and Indigenous land management in the Australian context is one of the most promising convergences in current environmental policy. Programs that pay Aboriginal land managers to manage fire in ways that reduce greenhouse gas emissions are already operating and demonstrating that the three objectives are mutually reinforcing. The expansion of these programs to include vegetation restoration carbon crediting would extend the logic of that convergence further. potentially providing the economic basis for restoration at a scale that no other funding source currently contemplates. Number 33. The rivers that flow underground. The visible rivers of the Australian interior are not the only rivers. Beneath the surface of the arid zone, in the rock formations and sediment layers that underlie the landscape, there are vast quantities of water that accumulated over thousands of years from rainfall events whose magnitude and frequency had no modern equivalent. This fossil water, stored in the aquifers of the Great Artesian Basin and other subsurface formations, has been used by pastoralists since the 19th century to support livestock in areas far from any permanent surface water. The artesian bore, the technology that allowed this water to be brought to the surface, was first developed in Australia in the 1880s and spread rapidly across the interior as the solution to the water problem of pastoral expansion. Within decades, thousands of bores had been sunk across the pastoral zone, drawing water from aquifer systems that had been accumulating their reserves for tens of thousands of years. The mound springs that had previously been the only surface expression of this deep water, and that had been critical water sources for Aboriginal communities and for the extraordinary specialized ecosystems that had evolved around them, were dewatered as the artesian pressure that sustained them was reduced by extraction. The mound spring ecosystems of the Great Artesian Basin margin are among the most ecologically significant and least known ecosystems in Australia. They harbour plant and animal species found nowhere else on Earth, species that have evolved in isolation around these unique, constant temperature freshwater sources over millions of years. As artesian pressure declined through the 20th century, many of the smaller springs stopped flowing, the ecosystems they had sustained shrank or collapsed. The species they harbored became critically endangered or extinct. The capping of artesian bores, a program pursued by the Australian government from the late 20th century to reduce uncontrolled water loss from bores that had been left flowing freely for decades, partially restored artesian pressure in some parts of the basin, and some springs have recovered flow as a result. But the aquifer systems themselves, the underground reservoirs that took tens of thousands of years to fill, are being drawn down by continued extraction and are not being recharged at any rate that would make long-term sustainability possible at current extraction levels. The fossil water of the Australian interior is, like the fossil fuels of the geological record, a finite resource that is being spent at a rate incompatible with indefinite continuation. Number 34. The country at the edge of recovery. There are places in the Australian interior where the story is different. Not completed, not resolved, but visibly and measurably moving in a better direction than the broader trajectory described throughout this script. These places deserve attention not because they represent the norm, which they do not, but because they demonstrate the possibility that the norm contains, and because the specific factors that have produced better outcomes in them are factors that can, in principle, be replicated elsewhere. The Indigenous protected areas of the Northern Territory and South Australia are perhaps the most important of these. These are areas where Aboriginal communities have asserted their management authority over the country they have always known, where cultural burning practices have been reinstated, where introduced predator control and feral herbivore management are conducted with the consistency and local knowledge that only sustained community management can provide, and where the ecological consequences of that management are measurable in the recovery of native mammal populations, native plant diversity, and fire regime health. The contrast between the ecological condition of indigenous managed areas and adjacent areas under conventional land management is, in the best studied cases, stark. Native mammal species that are declining or extinct across much of their former range persist in higher numbers in areas under indigenous management. Fire scar patterns in indigenous managed areas show the mosaic of different age burns characteristic of traditional burning, in contrast to the uniform fuel accumulation that characterizes areas where burning is suppressed or conducted only as emergency hazard reduction. The ecological evidence is clear enough that it has generated a significant scientific literature and has begun to inform policy at state and federal government level. The pastoral properties that have been converted to wildlife conservation through the work of organizations like the Australian Wildlife Conservancy provide another model of what is possible. The removal of cattle and feral herbivores from large areas, combined with intensive management of introduced predators and targeted restoration of native plant communities, has produced recovery of native biodiversity that surprises even experienced ecologists. Species that had not been recorded on some properties for decades have returned within years of the management change, drawn by habitat that was finally suitable for them after generations of degradation. These examples are not sufficient evidence that the crisis of the Australian interior has been solved or is being solved at the scale needed. They are proof of concept. They demonstrate that recovery is possible, that the ecological potential of the landscape has not been permanently lost, that the knowledge needed to support recovery exists. They are the beginning of a sentence whose completion depends on decisions not yet made. Number 35, the long arc of the landscape. When geologists look at the Australian continent, they see something that no human eye has ever observed directly. The full arc of time across which this land has existed and changed. They see a continent that has been near the poles and near the equator. They see a continent that has been wetter than the Amazon and drier than the Sahara. They see a continent that has been covered by sea and one that has been desert for 30 million years at a stretch. They see a land that has survived everything the planet could throw at it, and that still, despite everything, contains within it the potential for extraordinary biological productivity when the conditions are right. The resilience of the Australian continent is geological fact. It has survived ice ages and hot periods, catastrophic asteroid impacts and the extinction events that followed them, the breakup of Gondwana, and the slow drift to its current position. It has been through worse than what European settlement did to it. It has recovered from worse. But those recoveries operated on geological timescales. They were not achieved in decades or centuries. They were achieved in millions of years through the slow evolution of new life forms adapted to new conditions, through the gradual stabilization of new ecological relationships in the aftermath of catastrophic disruption. The recovery that the Australian interior needs now is a human recovery, achieved on human timescales by human choices and human actions. The geological resilience of the continent does not guarantee that recovery. It only guarantees that the potential for recovery exists, that the land is still there beneath the degradation, still containing the mineral substrate and the partial biological communities, and the intermittent rainfall that could, with the right management, be assembled into something that functions, The question of whether the will exists to pursue that assembly is a political question, an economic question, a question about values and priorities, and whose knowledge is considered valid and whose rights are recognized. It is a question that is being answered incrementally and imperfectly in every land management decision made in the Australian interior, in every water allocation, in every pastoral lease renewal, in every fire management plan, in every conversation between an Aboriginal elder and a government land manager about how a particular piece of country should be burned. The answers being given right now are mixed. Some are better than they were a generation ago. Some are not good enough. None of them are final. The landscape will continue to be shaped by the decisions that are made in the next generation and the generation after that, just as it was shaped by the decisions of the colonial era and the indigenous era before it. The arc of the landscape is long. What we do with the next part of it is still genuinely up to us. Number 36, the saltbush and the stubborn survivors. Not everything in the Australian interior has simply collapsed under the weight of what European settlement imposed on it. Some plants and some animals have proved more resilient than the dominant narrative of ecological collapse might suggest, not because they were unaffected, but because they possessed qualities that allowed them to persist, reduced and changed through conditions that eliminated less adaptable species. The saltbush communities of the semi-arid south are among the most significant of these stubborn survivors. Saltbush, the common name for species of the genus Atriplex and related genera, is one of the most stress-tolerant native plants of the Australian interior. It can grow in saline soils that would kill most other plants. It can survive extended drought that would desiccate species with less effective water conservation mechanisms. It can recover from heavy grazing, not completely and not without long-term consequences, but more reliably than the more productive perennial grasses that it shares the landscape with. The saltbush country that covers large areas of the semi-arid pastoral zone is not the pre-European landscape. The pre-European landscape in many of these areas was a more diverse mix of perennial grasses, forbs and shrubs in which saltbush was one element among many rather than the dominant species. The current dominance of saltbush in many areas reflects the selective pressure that heavy grazing imposed on the plant community, eliminating the grasses and forbs that could not tolerate heavy grazing while leaving the saltbush, which sheep and cattle find less palatable and which can recover from grazing more readily than many other species. But the saltbush community, however simplified compared to what preceded it, is not ecologically dead. It still supports a range of native animal species, some of which have adapted to the saltbush-dominated landscape with a flexibility that indicates something of the evolutionary plasticity of Australian fauna. The southern hairy-nosed wombat, one of Australia's largest surviving burrowing marsupials, occupies saltbush country across a significant area of South Australia. It has survived in a landscape that has been heavily modified by grazing, not because it was unaffected by that modification, but because it was flexible enough to persist in the modified conditions. The persistence of these stubborn survivors in degraded landscapes is both encouraging and instructive. It is encouraging because it demonstrates that the ecological potential of the Australian interior has not been entirely eliminated by the degradation of the past century and a half. It is instructive because it demonstrates that what survives degradation is not a random sample of what existed before, But the species and communities that happen to possess qualities, stress tolerance, reproductive flexibility, habitat generalism, that allow them to cope with conditions their ancestors never experienced. The survivors are not the typical pre-European species community. They are the exceptional ones, the ones whose qualities happen to align with the requirements of survival under European land use. Number 37. The sound of the country, the soundscape of the Australian interior before European settlement, is something that no living person has heard. It is something that can only be reconstructed, imperfectly, from the historical descriptions of early explorers, from the acoustic ecology of the few relatively intact areas that remain, and from the accounts of Aboriginal people who have lived long enough to remember when the country sounded different. What those sources describe collectively is a landscape that was not quiet. It was not the silent, empty landscape that the word desert conjures in most minds. The native grasslands before their destruction were alive with insects. The birds that inhabited them were numerous and varied. The mammals that moved through them, the native rodents and wallabies and wombats, contributed their own sounds to the acoustic environment. The rivers that ran through the interior before they were slowed and silted had the voice of moving water. The acoustic impoverishment of degraded landscapes is a real phenomenon that ecologists studying soundscape ecology have documented with increasing rigor over the past 2 decades. A degraded pastoral landscape in the Australian interior produces a soundscape that is measurably less complex, less diverse, and less energetic than the soundscape of the same landscape under intact native vegetation. The biological diversity that generates sound is less. The diversity of habitats that support different sound-producing species is less. The landscape is literally and measurably quieter. The recovery of acoustic complexity in restored areas provides some of the most immediate and emotionally resonant evidence of ecological recovery. When native vegetation is restored and native animals return to it, the soundscape changes in ways that people can hear without any specialized equipment. Bird song diversifies, insect noise increases and changes in character. The landscape becomes richer in sound as it becomes richer in life. For people who have known a landscape before and after restoration, the change in its voice can be as moving as any scientific measure of recovery. The knowledge of what the Australian interior used to sound like lives, partially, in the memories of Aboriginal elders who grew up on country that was less degraded than it is now. The sounds they describe of particular bird species in particular places at particular times of year, of the water in particular rivers under particular flow conditions, of the movement of particular animals through particular vegetation types, are ecological data as surely as any scientific measurement. They are data about what was there and therefore about what the landscape's potential contains. Number 38. The children who will inherit. Every generation that grows up in Australia grows up in a landscape that is more degraded than the one their parents knew, and less degraded than the one their children will know if the trajectory continues. This is not an abstract observation. It has specific consequences for how each generation understands what is normal, what is possible, and what has been lost. The phenomenon that conservation biologists call shifting baseline syndrome describes exactly this dynamic. Each generation accepts the ecological condition that it grows up in as the normal condition, the baseline against which change is measured. Species that were common a generation ago and that have declined by the time the next generation grows up are measured against the reduced baseline of the more recent generation rather than against the historical abundance of the earlier one. The total decline measured from the original baseline is systematically underestimated because each generation only sees part of it. In the Australian interior, shifting baseline syndrome has been operating for several generations. The Australians who managed pastoral properties in the early 20th century and who knew from their own experience what the country had been like before it was grazed heavily had a baseline that included knowledge of abundant native grasslands, diverse wildlife, clear rivers. Their children's baseline was the country as it was after the first generation of heavy grazing, already significantly degraded but still more diverse than it would be by the end of the century. The grandchildren's baseline is closer to what we see today, a landscape whose native diversity is a fraction of the original and that many people accept as the natural Australian condition. The breaking of shifting baseline syndrome requires access to information about historical conditions, the kind of information that this script has been attempting to provide. It requires the patient accumulation of historical records, the analysis of museum collections, the study of paleobotanical and paleoecological evidence, the listening to indigenous knowledge that allows each generation to understand not just the landscape they inherited, but the landscape that existed before what they inherited from. The children who will inherit the Australian interior a generation from now will inherit a landscape whose trajectory depends on decisions being made now. If the restoration projects currently underway are expanded to the scale they need to reach, if the cultural burning programs currently demonstrating their value are supported and extended, if the economic instruments that align private land management incentives with ecological sustainability are developed and implemented, the children of the next generation may inherit a landscape that is measurably better than the one being described here. That is what hope in this context actually looks like. Not the restoration of everything that was lost, which is not achievable on any human timescale, but the arrest of ongoing degradation and the beginning of a recovery that will take generations to complete, but that will be real in the first generation. Number 39. The country remembers. There is a quality of the Australian landscape that strikes many people who spend time in it. A quality of endurance and quiet persistence that is difficult to describe precisely, but that feels significant. The land seems, in some places and in some lights, to be waiting. Not passively, not hopelessly, but with the patience of something that has been through worse than this and that knows, in whatever way a landscape can know anything, that it has time. This is not mysticism. It is the ecological expression of a real phenomenon. The biological legacy of the pre-European Australian interior is not entirely gone. It lives in the seed banks in the soil, in the remnant populations of native plants and animals in refugia that degradation has not yet reached, in the mycorrhizal spores waiting in the soil for the roots of the right plants to associate with them, in the knowledge held by Aboriginal communities who have never stopped caring about country, even when they were denied access to it, in the genetic diversity of populations reduced but not eliminated by a century and a half of habitat destruction. The country holds these things. It holds them in the way that very old systems hold things, distributed across many scales and many forms, so that no single point of failure can destroy the whole. A population of native grass can be locally eliminated by overgrazing, and yet The species survives in a refuge 100 kilometers away, waiting for conditions that will allow its return. A knowledge system can be damaged by the death of key knowledge holders and yet survive in attenuated form in the memories of people who learned fragments of it in childhood and who, decades later, collaborate with linguists and ecologists to reconstruct what was partially lost. The system persists because it is distributed, and because what is distributed cannot be completely destroyed by any concentrated assault. This distributed persistence is the basis for the possibility of recovery. It is why the restoration projects described throughout this script are not futile exercises in nostalgia, but genuine contributions to the rebuilding of systems that have not lost the capacity to function, even if they have lost the conditions under which they can fully express that capacity. The country remembers. The question is whether the people who live in it will create the conditions for that memory to become the future. Number 40. What comes after? We have traveled far in this script, from the pre-European landscape of Australia as it was, green and managed and alive with the intelligence of 60,000 years of human care, through the processes that transformed it into what it is today, and to the beginning of the long, difficult, necessary work of understanding what was lost and beginning to restore it. We have looked at fire and soil and water and grassland and forest and animals and knowledge. We have looked at the political economy of destruction and the economics of restoration. We have looked at the technology of satellites and the wisdom of elders. We have looked at termites and topsoil and language and dust. What emerges from all of this looking is a picture of a landscape that is neither naturally what it has become nor permanently committed to remaining what it is. It is a landscape in a specific phase of a long story, a phase that began with European settlement and that is still, despite everything, not finished. The ending of this phase is not predetermined. It depends on choices that are still being made. The choices are not simple. They involve economics and politics and competing interests and institutional inertia and a legacy of injustice that has not been fully addressed and a scientific understanding that is still incomplete. They involve the recognition of Indigenous rights and knowledge in ways that Australian society has historically resisted and is only beginning to accept. They involve the willingness to invest in long-term ecological recovery in the face of short-term economic pressures that operate in the opposite direction. But the choices are real. The tools for making better choices exist. The knowledge for making better choices exists. The demonstration projects that prove better choices are possible exist. What remains is the accumulation of political will, economic incentive, and institutional capacity to make those choices at the scale the crisis requires. The Australian desert is not natural. It is made. And what is made can, over time, be unmade. Not completely, not in any single generation, but gradually, measurably, in the right direction, by people who understand what was here and who are committed to the patient work of helping it return. That is the story of the Australian interior. It is a story that is not over. And the chapter that comes next is still being written. Sleep well and know that somewhere in the red country of Australia's heart, there are seeds in the soil waiting for the right moment to grow. Number 41. The mycorrhizal web and the underground world. Below the cracked surface of the Australian desert, in the few centimeters of soil that still hold residual moisture after a rare rainfall event, a drama plays out that has no witnesses and receives almost no attention. It is the drama of the mycorrhizal network attempting, in conditions far below its optimal range, to maintain the connections between plant root systems that allow the desert's sparse vegetation to function as something more than a collection of isolated individuals fighting each separate battle for survival. The mycorrhizal web that underpins functional plant communities is among the most complex biological structures produced anywhere on Earth. In an intact native grassland or woodland ecosystem, the fungal threads connecting plant root systems create a network of communication and resource sharing that spans hectares. Plants connected to this network are fundamentally different from plants that are not. They have access to water and nutrients from a much larger volume of soil than their own roots can reach. They receive warning signals when neighboring plants are attacked by herbivores, allowing them to mount chemical defenses before the attack arrives. They can transfer photosynthate, the sugar produced by photosynthesis, to neighboring plants that are in shade or under stress, effectively subsidizing their neighbors' survival during difficult periods. This is not cooperation in the human sense. It is ecology. It is the result of millions of years of coevolution between plant species and fungal species in a specific environment, producing a system of interactions that is more complex and more beneficial to the participants than simple competition for the same resources. The system works because the participants are not competing for exactly the same resources in exactly the same way. The diversity of species involved in the network ensures that the network as a whole is more efficient at using the available resources than any collection of competing individuals could be. The degradation of the Australian desert has disrupted this network at scales that are difficult to comprehend. The loss of the perennial plant communities that anchored the network through overgrazing, vegetation clearing, and the introduction of plants that do not form the same mycorrhizal associations as the native species has fragmented the network from a continent-spanning system into isolated patches separated by areas where the network is absent or severely diminished. The plants in those isolated patches have fewer connections, access to smaller volumes of soil resources, and reduced capacity to survive the stress events, the droughts, the pest attacks, the extreme temperature events that the Australian interior delivers with increasing frequency as the climate changes. The restoration of a mycorrhizal network in degraded areas requires time and the right biological material. It cannot be achieved by planting native species alone, because the fungal partners that form the network are not present everywhere in the soil and do not spread quickly on their own into areas from which they have been absent. Active inoculation with appropriate mycorrhizal fungi is increasingly used in restoration planting projects, and the results demonstrate that inoculated plants establish faster, grow more vigorously, and survive drought stress better than uninoculated plants in the same conditions. The network, once established, expands. The investment in getting it started pays dividends for decades. Number 42, the documentation of what is disappearing. There is a race being run in the Australian interior between the pace of ecological knowledge accumulation and the pace of ecological loss, and at the moment the loss is winning. Species are declining and disappearing faster than the scientific community can document the detailed ecology of each one. Knowledge holders in Aboriginal communities are dying without having passed on everything they know to the next generation. Ecological communities that have never been thoroughly surveyed are being cleared or degraded before their full biological composition is known. The Australian interior is losing its contents faster than any inventory can keep up with. This is a form of loss that is different from, and in some ways more final than, the physical loss of vegetation or soil or water. The physical losses can, in principle, be reversed by processes that are understood and that are being applied in some places at some scale. The knowledge losses are harder to reverse because knowledge, unlike vegetation, is not stored in the soil waiting for the right conditions to germinate. It lives in minds, and when the minds that hold it are gone, the knowledge is gone with them, unless it has been transmitted. The urgency of documentation, of the systematic recording of indigenous ecological knowledge in forms that can survive the deaths of current knowledge holders and be accessible to future generations is widely acknowledged. Programs for recording and preserving indigenous languages, ecological knowledge, and cultural practices associated with land management have been funded and have produced valuable results. But the scale of the effort remains inadequate relative to the scale of the challenge, and the pace of loss of knowledge holders continues to outpace the pace of documentation. The documentation effort also applies to the biological record. The thorough survey of the ecological communities of the Australian interior is an incomplete project, even after more than a century of scientific investigation. New species continue to be described from museum collections and from targeted surveys of poorly known habitats. Genetic studies continue to reveal cryptic diversity hidden within what appeared to be single species, but turn out to be multiple distinct lineages with different ecological requirements and different conservation needs. The ecological community that existed in the Australian interior before European settlement is not fully known, and it never will be, because too much of it was lost before adequate documentation was possible. What can be done now is to document as thoroughly and as urgently as possible what remains, to treat the ecological knowledge held in Aboriginal communities as the scientific resource it is, and to invest in the surveys and the language programs and the knowledge recording initiatives that preserve as much as possible of what is still available to preserve. This is unglamorous work. It does not make international news the way a catastrophic wildfire does, but it is as important as any more visible conservation action, because everything else that might be done to restore the Australian interior depends on knowing what was there and how it worked. Number 43, the invitation. This script has covered 42 specific aspects of the story of the Australian desert, its origins, its causes, its consequences, and its possible future. 42 is a lot, and yet it is a fraction of the full story. Every number in this list could be expanded into an entire documentary. Every landscape feature, every animal species, every aspect of the knowledge system described here has a literature of its own, a community of researchers and practitioners and knowledge holders whose life's work is devoted to understanding it more deeply than a single script can convey. The invitation that this script extends is not to accept what it contains as the complete picture. It is to begin paying attention to the landscapes you move through and to the histories those landscapes carry, to begin asking questions about what was there before, about who managed it and how, about what was lost and what persists, to begin noticing the silences in landscapes that should be richer, the bare ground where dense vegetation should be, the rivers that should run clear but run brown, the skies over the interior that should be full of birds but are not, The Australian desert is not natural, but understanding that is only the beginning. The more important question, the question that the 42 numbers of this script have been preparing, is what comes next. Who decides? Who manages? Whose knowledge leads? Who pays? Who benefits? Who is responsible? These are questions that do not have answers in this script because they do not have answers yet in the world. They are being answered imperfectly and incompletely in the politics and economics and science and community activism of Australian society right now. And the people who understand what is at stake have a responsibility to be part of that conversation. If you watch this video to the end, you understand something now that most people do not. You understand that the landscape of the Australian interior is not a natural given but a human consequence. The consequence of choices made by the people who managed it over the past 200 years. And you understand that the choices being made now will determine the landscape that the next generation inherits. That is a weight, but it is also a form of power. Knowledge is the beginning of agency. Understanding the problem is the first step toward changing it. And the story of the Australian desert, as this script has tried to tell it, is not primarily a story of loss. It is a story of potential, of a land that has survived extraordinary damage and that still contains within it the biological and cultural and scientific resources needed to begin its recovery. The recovery will not be complete in any lifetime now living. It will not be easy. It will not be cheap. It will not be achieved without confronting the political and economic arrangements that produced the degradation in the first place, and that, in significant respects, are still producing it. But it is possible. And possibility, understood clearly and acted on with persistence and intelligence and humility before the knowledge that already exists, is enough. Sleep well, the land is still there, and it is still asking. Number 44, the carbon below the surface. There is something hidden beneath the red surface of the Australian outback that most people never think about when they picture those flat-baked plains stretching to every horizon. It is not water, though water is there too, deep and ancient and slowly being drawn down. It is carbon, locked carbon, carbon that the living systems of the pre-European interior accumulated over thousands of years, and that the degradation of the past century and a half has been steadily releasing back into the atmosphere. The soil carbon story in the Australian interior is one of the most significant and least visible aspects of the continent's ecological crisis. Soil carbon is not a glamorous subject. It does not photograph well. There are no striking images of soil carbon loss the way there are striking images of topsoil blowing away in dust storms, although the two phenomena are related. But the loss of soil organic carbon from degraded Australian soils is a real and ongoing process with consequences that extend from the health of the degraded soil itself to the global atmosphere that receives the carbon the soil releases. Healthy native grassland soils in the Australian semi-arid zone contain organic carbon accumulated over thousands of years of plant growth, root decomposition, and microbial activity. The carbon is not uniformly distributed, but is concentrated in the upper layers of the soil profile, where the root activity is most intense and where the organic matter input from surface litter is greatest. This upper soil carbon pool is the most biologically active, the most important for soil fertility, and the most vulnerable to loss. Overgrazing removes the plant cover that inputs organic matter to the surface and reduces root turnover in the soil. As organic matter inputs decline, The soil microbial community that processes them declines in turn. Soil carbon content falls. The fertility of the soil falls with it. The capacity of the soil to hold water, which is partly a function of its organic matter content, falls. The soil becomes less functional in every measurable way, and the carbon that was stored in it, accumulated over thousands of years, enters the atmosphere as carbon dioxide released by the organisms that decompose it in the absence of fresh organic matter to replace it. The reverse of this process, the accumulation of soil carbon under restored native vegetation, is both possible and measurable. Research on the carbon sequestration potential of restored Australian grasslands has produced estimates that vary widely depending on climate zone, rainfall, and the quality of the restoration achieved, but the direction is consistent. Restored native perennial grasslands managed without heavy grazing accumulate soil carbon at rates that are modest in absolute terms, but that, applied across the millions of hectares of degraded pastoral land that could potentially be restored, add up to a nationally and globally significant contribution to climate mitigation. The possibility of generating carbon credits from grassland restoration is now being explored by a number of projects across the Australian interior, with methodologies being developed that can measure soil carbon changes with sufficient precision and certainty to support crediting. The financial return from carbon credits could provide the economic basis for restoration at scales that no other funding source currently contemplates. A landscape that has been described throughout this script as an ecological liability could become, through the combination of ecological restoration and carbon finance, an ecological and economic asset. This is not utopian. It is the direction that several current projects are pointing, and the direction that a serious policy response to both the ecological crisis and the climate crisis in the Australian interior would need to pursue. Number 45. The stories that hold the land together. In the end, every piece of knowledge described in this script, every ecological fact about perennial grasslands and mycorrhizal networks, and cultural burning and soil biology, ultimately connects back to a set of stories, not scientific papers, although the science is there and it matters, not government reports, although the reports document the damage and point toward the remedies, stories, the living narratives through which human beings understand their relationship with the world they live in and their obligations to it. The stories that Aboriginal Australians have told about their country for 60,000 years are not incidental decoration around the practical ecological knowledge those stories contain. They are the vehicle through which that knowledge has been transmitted, refined, and applied across generations. The dreaming story that describes the specific behavior of water in a particular landscape is not separable from the practical knowledge of that water's behavior. The ceremony that maintains a human community's relationship with a particular plant species is not separable from the management practices that maintain the health of that plant community. The song that encodes the route between two water sources is not separable from the geographical knowledge of that route. Story and knowledge and practice are integrated in a way that Western scientific tradition, which separates its stories from its data, sometimes struggles to understand. The stories that European Australians have told about the Australian interior are different, and the difference matters. The dominant story has been a story of conquest and improvement, of civilization advancing into wilderness. of productive land being created where there was nothing. This story erased the civilization that was already there, dismissed the management that had maintained the landscape, and misunderstood the ecological consequences of what the advancing civilization was doing. It was a story that made the destruction possible by making it invisible. Changing the story of the Australian interior does not require replacing one simple story with another. It requires expanding the story to include what was left out, the 60,000 years of indigenous management, the complexity of the ecological systems that management maintained, the deliberate and gradual nature of their destruction, and the possibility and the necessity of their partial restoration. It requires making visible what was made invisible, naming what was unnamed, valuing what was dismissed. This script is one small contribution to that expansion. It is addressed to anyone who has ever looked at the Australian desert and accepted it as natural, who has assumed that the red emptiness of the interior represents what Australia always was and what it will always be. It is an invitation to look again, to see in the dust not a natural condition but a human consequence. To see in the silence not primordial emptiness, but the absence of what was there before, and what, with enough time and enough commitment and enough respect for the knowledge that already exists about how to bring it back, might be there again. The land is not lost, it is changed, and what is changed by human choices can slowly be changed again by better ones. That is the story the Australian desert is asking us to understand. It is a story about responsibility, about the obligations that come with occupying a landscape, and the knowledge that those obligations have been inadequately met, about the possibility of meeting them better in the time that remains. Sleep now, the country is patient. It has been waiting for a long time, and it can wait a little longer, but not forever. The seeds in the soil will not wait forever. The knowledge in the minds of the elders will not wait forever. The window in which the worst outcomes of the degradation described in this script can still be avoided is not unlimited. The desert is asking. The question is whether we are listening, and if you found this journey valuable, share it with someone who has never thought twice about the red center. The most powerful act of conservation is also the simplest, helping another person understand what is at stake.